Hello, Professor Monica Conti. Are you here with us?
Hi Jenny, how are you? Hi. Hi. Fine, thanks. And you?
Fine, fine. So now we are going to start with
Monica Conti?
with Monica Conti, who actually you have
Yes.
invited.
Yes.
Do you want to make the presentation of Monica Conti?
No, it's okay if you make it. Don't worry.
I I am scared to do that, but okay. In which city of Italy are you these days, Jenny?
Now in Bari, in
Okay.
Puglia, since I made my PhD course in Bari.
Oh, wow. Amazing.
Yeah,
Okay,
but
so we have with us also Professor Monica Conti.
ciao Monica.
Ciao, ciao Jenny. Hello, Duan.
Hello,
Here
Professor
I am.
Conti. How are you? Here just saying hello to Jenny, who actually has invited you for our conference. It's really a great pleasure that you have accepted
For
the
me, it's
invitation of
fantastic
Jenny,
to be here.
and
Thank you
also
very
our
much.
invitation. Thank you.
I'm really
Okay.
very honored to be here.
Hi, everybody. Hi, Monica.
Hey,
That's
Susanna, ciao.
Susanna.
Ciao
Ciao.
Susanna.
Ciao.
So we have for this conference a long list of Italian mathematicians as speakers. So before also was Luigi Rodino. Later will be Cristiana De Filippis.
Yes,
Professor
tomorrow.
Monica Conti is here. Professor Susana Terracini. So very good. Okay, good. So maybe Professor Conti, if you want, maybe
I
you
try
can
to
start
share the
sharing your
slide.
screen. Yes.
Um, okay, let me. Can you see?
Yes.
Okay.
Okay, still we have some minutes, 6 minutes to start. If you want, you can keep your screen share.
I'm trying.
Okay. Do you want to keep like this or in full screen mode?
Full screen, that is Control L. I guess. No.
I guess yes.
Uh, bu- 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 Just a minute. Senti full screen questo.
Aspetta che io adesso sono Mac user.
Perfetto, grazie mille.
Di fare un seminario? Ah, mi collego? Ah, sì. Ah.
Okay. You want maybe to try, Professor Conti, to see if you can move your slides correctly?
But are you seeing the slides?
I see your slides, yes, but
Okay, since
maybe you want to...
I cannot see them, so I'm a bit in trouble. Maybe I have to interrupt
okay.
and to share again. Okay, now now it's closed. I don't understand. Just a minute, sorry.
Don't worry, we have time.
Okay. Okay, now we have the same problem and I don't know. Okay, maybe we can keep this visualization because I'm not able to move otherwise.
Okay.
You can
I
see
think
the
it's
slide.
visible. Yes, it's visible.
It's okay, it's
Yeah.
moving?
Yes. The
Okay.
slides are moving, yes.
Okay, but it's just going down. Sorry. Okay. Okay.
Nice background of the slides. Nice background.
Thank you very much.
Okay. Just let me recall Professor Monica Conti. Only speakers and shades of sections are following us in the Zoom platform, right? But participants are following us by YouTube, so they are going to be able to make questions,
Okay.
and then we are going to communicate the questions with you, right?
Okay.
You can take 45 to 50 minutes if you prefer, right? Plus 5 minutes of questions.
Okay.
So very good. I think then we can start. It's really my great pleasure to introduce the first speaker today, Professor Monica Conti. Professor Monica Conti is an Italian mathematician, full professor of mathematical analysis at Politecnico di Milano. Her research concerns nonlinear elliptic and evolution partial differential equations, infinite dimensional dynamical systems, and equations with memory. Currently, she is focused on phase field models for the description of phase separation in complex systems with emphasis on the Cahn-Hilliard equation. In addition to her research, she is actively involved in teaching innovation and dissemination, in particular throughout the podcast, Inventing Mathematics, Stories of Women and Men in Mathematics of the FDS Lab Department of Mathematics. So thank you very much, Professor Monica Conti, for being here, and please continue with your talk with title The Cahn-Hilliard Equation with Nonlinear Diffusion Beyond Convexity. Thank you very much.
Thank you very much for your invitation. It's really an honor for me to be here and a special pleasure. So thank you very much to all the organizers, also for the opportunity to share with you recent advances of my favorite equation. It is the Cahn-Hilliard equation. But let me start with the physical phenomenon that we are interested in this talk, that is phase separation. Phase separation is a spontaneous process that leads to different substances in a mixture to self-organize in homogeneous phases, creating distinct regions. As you can see, each with a higher concentration of one of the two components. And the familiar example on the right is simply oil and water in a salad dressing. After shaking, we all experience that they appear well mixed. The blend seems to be completely well mixed and done. But after a while, small bubbles appear and oil and water spontaneously separate almost completely. And the same phenomenon, as you can see, appears in much complex systems like binary alloys that you see in the first line, or in polymers like the green hydrogel that you see here that is commonly used in our mixing creams. And you can also appreciate the fact that during time, a long time, phase separation happens in two stages. The first one is called spinodal decomposition that happens immediately after the mixture becomes unstable. So particles start moving and small fluctuations grows in the material. And then in a second step afterwards, all domains evolve through coarsening. This means that smaller structure disappears while larger domains grow by reducing the amount of interface between the two components. Okay, so creating larger regions where one component, one material is dominant with respect to the other. And I have also a numerical simulation that it is done with our favorite equation, the calendar one, where you can see perfectly depicted this phenomenon, is illustrated this mechanism, showing the emergence of larger and larger structures over time, each dominated by one of the two components, let's say material A in the pink region and material B in the yellow region. The phenomenon that you are seeing here was first discovered and described in material science, and we are in the late 50s of the past century, but nowadays is used to design new materials, so is a pillar of engineering science. But nowadays we know that the mechanism is much more universal, and indeed we know that phase separation plays a fundamental role in the organization and function of living cells. And this discovery is so important, it was awarded in 2023 with the Breakthrough Prize in Life Sciences for the potential to yield important advances in medicine, because knowing better this central mechanism in the organization of cells can, of course, give a better understanding of disease mechanism with the potential of identification of novel biomarkers and also novel therapeutic approaches. But our job is doing mathematics, so with these physical motivations in mind, let me introduce the mathematical framework, that well-established one that we use today to describe phase separation. We call this the Caniller paradigm, that consists in introducing an order parameter that is the local composition of the mixture. So this phi that is our unknown is essentially the difference of the concentration already normalized of material A and material B, material 1 and material 2. So the range of phi is between -1 and 1, where 1 and -1 represent the pure phases of one of the two material. Then, as you can see in the simulation, we have conservation of mass, meaning that the average of phi remains the same of the initial datum that starts with the evolution. And then we describe the evolution of the system as driven by decreased minimization of a certain Ginzburg-Landau free energy. A look to the Ginzburg-Landau free energy that we are considering here. We have two parts that are essentially competing among them. The first part, the red one, is with a constant that is named the interfacial stiffness of the system, is penalizing, in a sense, phase separation, because you see here we have a gradient, and when you jump from one material to the other, the gradient is large. So this is penalizing the formation and the presence of interfaces. But then we have psi, this double well potential. Double well potential means that the shape of our potential is double well with two minima, global minima at the same level, representing the best concentration of one component and the best concentration of the second component, best meaning at the minimum level of the energy. Okay, so the system evolves trying to assume the concentration typical of the red point, of the blue point. Why the system cannot choose to go to a single minimum of the potential, but because of mass conservation. So the system cannot choose to stabilize everything on one single minimum of the potential, but have to share the space because the mass of the system remains with the same average along the evolution. So what happens in this competition, let me move, okay, is that what we observe is exactly what is on the right. While so the system evolves optimizing, in a sense, this setting. The strategy is the optimal one with the constraint of mass conservation. So first, the material starts separating, and this is to reach concentration corresponding to the two minima of our potential. But now that psi is essentially at the minimum level, what you can do to minimize the whole free energy is to reduce the interfaces. So the cost, the energetic cost given by the red part to create interface. So if you lower that, decrease the length of the interfaces between the two components, you are doing better for your energy. You are saving energy. So we have this compromise, and I think that this model can describe quite well what we saw in the simulation. If you use this machiner here and you proceed, you end up with the famous and celebrated Cahn-Hilliard equation. That is a system, in fact, that you can find in the original paper by physicists John Cahn and John Hilliard. We are in February 1958. Is a system, as I told you. You can see the first equation that is essentially a continuity equation saying that phi, our variable, the phase state, evolves through a diffusive flux that is driven by the gradient of the chemical potential mu with a certain constant mobility m that is positive. The second equation is prescribing, is an assumption that the mu, the chemical potential, is in fact the variational derivative of the energy we are dealing with. And then you have no flux boundary conditions that are in fact ensuring across the boundary. So this is ensuring that the mass is globally conserved over our domain. Notice that if you substitute the second equation in the first, you end up with a single equation, the Cahn-Hilliard equation, that is a fourth order nonlinear parabolic equation for our phi. Okay. Mathematical features, the basic ones, everything starts from here that you want to preserve with the model, and we can check it easily. We have energy balance, so the energy is decreasing a long time, and you can test, simply check this by testing the first equation times mu and the second times the derivative of phi, and you sum it up, and you end up exactly with this relation. And of course, mass conservation follows by the conditions on the boundary, simply integrating over omega, the first equation. So we are safe with our prescription that we have in the modeling. They are saved in this final equation that you saw here. What can I say about this? Okay, a closer look to psi. There is a precise psi that we want to take in consideration. It is the Boltzmann-Gibbs potential, where you see the logarithmic part, this big F, is highly singular and accounts essentially for minus the entropy of mixing of the system. So it is the physically relevant potential that we can consider, minus this quadratic perturbation. Here, theta and theta naught essentially represents in the modeling to temperature. Theta naught is fixed, is typical of the material. And you can see that if theta is small enough and goes below this threshold temperature, then the potential becomes double well-shaped and phase separation can start. This is exactly what you see in the phenomenon. You first mix, so the temperature is growing up, but then you let the mixing without any movement, so the temperature decreases, and then phase separation immediately starts. So this is our potential. Good news, with this potential that is singular in -1 and 1, the derivative in particular, you are safe from the mathematical point of view because phi, your variable, takes value in the physical interval -1 and 1. You don't have to care to do a priori estimates. You are already there. Of course, you have to pay a price because this psi, the component f of the psi, is highly singular, and this highly singular is a bad news in the sense that you can see this relative growth condition of the second derivative with respect to the first one that is exponential will cause trouble when trying to do smoothing estimates for our solutions. Okay, let me give you, okay, sorry for this, but a very quick overview on the literature for what it is important for my talk. Nowadays, the behavior, the mathematical analysis of the standard classical Cahn-Hilliard equation that I presented is very well established with some just few small issues that I'm going to present. We have global existence of weak solutions as soon as you start with initial datum with finite energy. Solution for us means something that lives in H1 and remains, in fact, almost everywhere far from the pure phases +1 and -1. we can prove this. We have certain uniqueness of weak solutions, and here the fact that the mobility is constant plays an essential role. We have then the equation is parabolic, so we expect to have smoothing in time, and in fact we have instantaneous smoothing for our unknown that becomes W to 6 in omega. 6 is the critical exponent in dimension 3. Of course, if you are in dimension 2, this is W to P for any P that is not infinity. And then we have a very complete regularization as it is for the ith equation, provided that omega is smooth enough, of course. And here's something strange, an issue. If you are in 2D, this full regularization up to the regularity of your domain is instantaneous when you are in 2 dimensions. This means that it happens on tau infinity for every tau positive, while this issue is completely open, and it is a big issue in 3-dimensional domain. Of course, this is in connection with the knowledge of the fact that phi remains really strictly separated from plus and minus 1 as it is for the 2D case. But I do want to insist on this. We will go back on this. And concerning the long-time behavior, you can study a lot of stuff, attractor and so on. What is relevant for this seminar is the fact that every single trajectory of our classical Canadian system converge to an equilibrium. It is able to select one single equilibrium, a stationary state of the energy, as time goes to infinity. Just me give you a very quick list, very much incomplete, concerning people working over 40 years on the classical Canadian equation. There is the German school with Abels and Garke and Wilke, very active with fundamental results, and Italian school, of course. And in bold, you see the name of Alain Miranville that gave a lot of contribution, but it is cited here because he had a wonderful monography about the Canadian where you can check what I'm saying and learning much more. And then there is a very nice review by Hao Wu for the Canadian equation with dynamic boundary condition, but where you can find the modeling in a very, very fine way. I love it very much. Okay. I want to give you some tips about the techniques that we use to reach our well-posedness theory, at least. Concerning global existence, I have to say that the energy balance that I showed you guides completely the analysis, because it is able to give us immediately important a priori estimates. We know that the energy remains bounded, meaning that the norm of the solution remains bounded. And this is important when you start with our approximation procedure, for instance, using a Galerkin scheme where we approximate the data, and we also approximate the singular potential by regular ones. Having a priori estimates is crucial. We have this integral estimate that is also uniform of time interval of unitary length, for instance, and this is important for running some uniform Galerkin lemmas. And then once we have these a priori estimates with the integral control of the gradient of mu, with elliptic estimates, so relying very much on the second equation, we are able, with a well-established machinery, to transfer integrability from the gradient of mu to mu itself to psi prime, the one that is in the equation, into the Laplacian of our solution. So in the end, we have some integral estimates for mu in H1, for psi prime in L6, and for the Laplacian. So we have some control of the kind L2 in time, L6 for the Laplacian. So essentially, we are in H2 with our solution almost everywhere. And as I told you, because of the very bad growth relation between psi prime and the second derivative of our potential, it is impossible from here to deduce any kind of estimate for the second derivative. And this is something that, of course, prevents our possibility to show instantaneous regularization in the 3D case. Uniqueness. What about uniqueness? Here I want to go a bit deeper, showing you the basic computation that we do to show uniqueness. So basic idea, we pick up any two solutions and fix the mass, the mobility equal to 1. You write down the equation for the difference, no problem at all. This is exactly what it happens. And now, taking into account that you cannot go to second derivative of psi, the only test that is admissible here, the third thing that you think is the only thing that you can do. So you test the second equation by the difference, phi1 minus phi2. This means essentially removing the Laplacian from the first equation. So we test the first equation by minus the Laplacian with Neumann boundary condition. Recall this. The inverse of this on functions with the zero mean. You do this and you end up with inequality that is written here with a, let's say, good term, this red one that counts by testing the Laplacian, and then the contribution of psi prime minus psi prime, where we have this good part, which is bad from the regularity point of view, but it is good from the point of view of the sign because f is convex. The derivative of the logarithmic part, okay? And then you have to pay this guy here, but now you feel happy because you can close the estimate simply estimating the L2 norm with the L2 norm of the gradient plus the H minus 1 norm of phi1 minus phi2. And this is exactly the H minus 1 in the space of function with zero mean as it is the difference phi1 minus phi2. And here you are in the position to close your estimate via a Cromwell argument. So you can see here, convexity of f is crucial, and also the fact that you can construct some positive norm of the gradient in the left-hand side coming from here. Closer look, because I want to reveal the role of the interface energy in this computation in order to possibly generalize the mechanism. So I write explicitly the interface energy. I compute first and second derivative. That means the Laplacian in the first derivative and the Laplacian in the second derivative. I rewrite the system. Now, the part with the Laplacian, I simply write the difference of j prime in phi1 and j prime in phi2. I do the same computation, but now I see that the red part, the good contribution is nothing but the test over phi1 minus phi2 of the difference of these two guys, the first derivative of j. And in order to close the estimate as above, what I need is that this guy here, that is essentially the second derivative, okay, of my interface energy at a certain point in between phi1 and phi2, when tested over phi, that is simply the difference, phi1 minus phi2, gives you something positive, more than positive. Gives you a constant times the gradient on phi. And once I have this, I can close my estimate. So what it is relevant for uniqueness is a double convexity for our f, our potential, and we have, and the strict, in fact, convexity of the interface energy, as given by this relation here. Okay, and here it starts the new part with some remarks about this convexity for the interface part of the energy, because what we want to do now is to push the potential of the Canadian equation to describe complex materials like crystal, polymers, and hydrogels that I showed you, because in that case, assuming that the interface stiffness is constant, is too lazy, okay, is not able to capture exactly what's going on, because the interface energy must depends in fact on the local composition. We use this word instead of being stiff. So the energetic cost of creating interfaces do depend on the local composition of the material. So the interface is not stiff, the cost is not the same, the interface is soft, and this is measured and captured by nonlinear coefficient here instead of the constant kappa. This coefficient, when it is high, we have an high cost of creating an interface, while when A is small, it is more convenient to create an interface in that point. And this is capturing very well what happens in hydrogen. And a typical example will simply take a quadratic polynomial approximation of everything. Of course, the first coefficient must be positive to reconstruct stiffness of the interface. So this is the energy that you want to deal with the test this new function here instead of the constant that you saw before. And if you run the same machinery and the same variational derivation for the model, nothing is changing. This is a new Canadian equation where the second equation, the equation for the chemical potential, that is the distributional derivative of our new energy now, it is okay, it is much longer, more complicated format, it is simply that. So this is the good model that you want to study also in a more physical sense, adding also a non-constant mobility in the first equation, the continuum equation. So we assume that the mobility, so this is the flux, B of phi times gradient of mu as before, but now B depends on phi. And this is the continuity equation. So this is the system that now we want to study and to tell something about this new system. So with two functions instead, the two constant, nonlinear diffusion A, and this mobility B here now depends on phi. Let us fix the assumptions. So we study the system now with the best situation. So non-degenerate nonlinear diffusion and non-degenerate mobility, meaning that they are, okay, sufficiently smooth functions that are bounded with this constant, but also bounded below by strictly positive constant. This is non-degeneration of both coefficients. Both are important for our analysis. Instead, we used the same Gibbs, Boltzmann-Gibbs potential, our favorite psi. So these are the standing assumptions. So the question is, what changes now that A is not constant? Let's focus on A. Okay, nothing at the beginning. Good news, the energy inequality also, we can run our Galerkin scheme and try to get existence. Also, the total mass of the solution is preserved over time. You can see it by the first equation. Simply integrate by parts on the domain using the boundary conditions. So no problem at all. Good news, but now, since the chemical potential gains a quadratic gradient term, as you saw before, what happens is that the gradient part of the energy, those famous J, may become non-convex even if you prescribe that the coefficient A here is convex, and I want to show you this. But this means that classical tools for uniqueness and then smoothing of the model based on convexity, as I showed you, dramatically fail. So let me convince you of this fact that the gradient part of the energy may become non-convex. So first, the literature, because if you go through the literature, although you can find millions of papers with Canillard in the title, if you go through nonlinear diffusion, you just find these two papers in the literature, and the curiosity, they are of the same year, 2013. In both papers, essentially that works with constant mobility, you can find the existence of weak solution in 3D domains. Uniqueness is just given in the second paper, but under these assumptions, that is convexity of the coefficient A, and this strong concavity assumption on the reciprocal of AY. Let me compute with you J. This is J. This is the first derivative, and this is the computation of the second derivative. And let me go to the second derivative. I want to test convexity. So I take my second derivative in the first line. I add and subtract this quantity. So I recognize adding the first, the second, and the last one with the plus a perfect quadratic part. So this is the square. Okay, this is the sum of two guys with the square. So this is not a problem. This is non-negative. And what remains is this guy here. We justify this A, and then the minus the blue term. You rearrange these guys, and you realize that you have A second, the denominator, A cubed, but this is positive because A is positive. And this is what remains is exactly the second derivative of 1 over A. So with a minus sign in front, under the assumption of Skimperna-Pavlov, you are showing the existence of a certain kappa tilde positive here that dominates the square, the integral of the square of the gradient. So you have convexity in the strong sense that we discussed before. The assumptions in Skimperna-Pavlov guarantee strict convexity of the interfacial energy. And this is why we can now easily prove uniqueness of solutions, because we know how the scheme is working, relying on convexity. So now, okay, is convexity is condition too strong? And essentially, yes, because very physically relevant choices of coefficient violate this convexity assumption. Just think to a quadratic stiffness like this, symmetric, because we assume that the material is symmetric in both components. You compute the reciprocal, you draw a picture, okay? This is our convex coefficient A, but when you draw your 1/A, that is the blue, the violet one, you see that the parameters are adjusted properly. You immediately lose the strong concavity of this 1/A. So the assumptions in skin-permeable are too strong for physically relevant application. And so our program now is try to say what it is possible to say in the non-convex regime. Take in mind that what we know at the moment is just the existence of weak solutions and nothing more. So what remains open, and our key open issue in the non-convex regime, are uniqueness of weak solution. We expect to have parabolic regularization, but we don't know how to prove it. Also, if it is possible to justify the energy equality instead of the inequality, it would be great, in particular for the study of the long-time behavior that you would like to analyze. And this is an open issue even in the convex regime due to the presence of this functional parameter A in front. And then the best would be to be able to prove the convergence of the trajectory to a single stationary state as t goes to infinity, as it is for the classical Canadian equation. Okay, let me start with the program. So this is our very ambitious program. I start by telling you what is a weak solution in our context, because I need some notation. So I fix the value of the mean, the average of phi that is conserved over time. This is the space of energy solution. So we are in H1, we are in L infinity because we take value just between -1 and 1. And the mean, this is F with the slash over, simply is the 1 over the mass of the area of omega, integral of phi over the domain omega. And this remains fixed during the evolution. Okay, what is a weak solution, a global weak solution? You start with a datum with finite energy, so it is in the space by M. And we know by previous papers that there exists a global in time weak solution, the pair phi and chemical potential. These are the regularities. So phi is L infinity in time with values in the energy space. We have some integrability in H2, as I showed you. Here the subscript U log means that the integral over t plus 1, let's say, of the H2 norm of phi is bounded by a constant that is uniform with respect to time. And also it is global in time. The time derivative has some regularity, is L2 in time with values in the dual of H1. This is not the dual of H1, this is the dual of H1, but when restricted to functions that have zero mean, that is the orthogonal, essentially the complement of functions having fixed average. Of course, we can show that we stay not far, but we cannot touch plus and minus 1, the pure phase is too much, and we have some integrability in H1 for the chemical potential, as I showed you before. And this is simple, the variational meaning of the first equation, while the equation for the chemical potential is satisfied essentially almost everywhere in our space-time cylinder. Okay. Let me tell you that the 2D theory about this molecule is very much complete, and we are particularly satisfied. And this result are quite recent and very recently appeared on the Journal of Functional Analysis in collaboration with my dear friends and Italian colleagues, Stefania Gatti from Modena, Andrea Giorgini here at Politecnico di Milano, and Giulio Schimperna from University of Pavia. Let's start so with the 2D theory. Now we fix our domain. Omega is a two-dimensional domain, and this is crucial. So it is a bounded domain with the boundary smooth enough. It depends on how much you want to push your regularity theory. Let's say that C3 is enough for what I'm telling you. We pick up a global weak solution according to previous paper that departs from our initial D2 phi naught that is fixed. And then at the first step, we can show that the solution satisfies an improved regularity that seem a small thing, but you will see it is crucial, we can prove that phi is not just in L2H2, but it is L4 in time. And also we can push regularity, since you are in dimension 2 for every exponent p greater than 2, but not infinity. We can show that our phase field variable becomes W2P for every P, and also the singular part of the potential, the derivative, becomes in some integrability with respect to LP in space. We can show uniqueness. That was our first goal. Sorry, here we have a mistake. Assume that the mobility, so this is B, is in C2. Take any two solutions originating from two distinct initial data. Why not? Fix the length of your time interval, big tau, and then you can show that there exists a constant such that the difference of your solutions, phi1 and phi2, in H-1 in the dual, is dominated by the difference of the initial data in the same space. So this is a continuous dependence estimate in a lower space that it is enough to tell you that, in particular, the weak solution is unique when you start with the same initial data. So we have uniqueness, but not only. Essentially, with the same trick, we are able to show that the system in 2D exhibits parabolic regularity, meaning that for any tau, immediately, any tau positive, immediately on the time interval tau infinity, the solutions is L infinity in H3. And also the time derivative becomes L infinity in the dual, sorry for this, and gains some integrability. The solution becomes completely continuous on the infinite cylinder and is strictly separated from the pure phase. Can you see here? There exists a delta, a positive delta, only depending on tau and on the norm of the initial datum, such that phi remains between -1 plus delta and 1 minus delta. This means that the solution never sees the singularities of the potential. And this is why we can run bootstrap arguments as soon as the domain is smooth enough to reach extra regularity and the full parabolic regularity for our solution. Of course, also the chemical potential gains some regularity. So the estimate that before was just in L2 becomes in L infinity with respect to time, and we gain extra integrability in H3 for the chemical potential. And after we are able to prove strict separation and parabolic regularity to go together, as I told you before, we are also able to prove that the energy identity, that is a fundamental tool to study the long time behavior, holds true. And we can do this by approximating our bad weak solutions with much more regular solution, saying that this equality is true on tau infinity, and then essentially we let tau goes to 0 and we completely reach the energy inequality. And if you survive to this, I would like to show you why in 2 dimensions we are able to recover uniqueness, just a detail, and showing you that this extra regularity L4H2 is essentially the gateway to control the nonlinear diffusion term and, for instance, prove uniqueness. Let's see if I succeed in giving you the message. So let me just focus on A. So I keep the mobility constant. Introducing the mobility is an item. Let's keep the mobility constant. Set a big phi, the difference of phi prime minus phi second. And you run the same computation as before. So you test the first equation by minus the Laplacian with Neumann boundary condition. And you end up with a certain equality that looks like the same as before, with a good red part, with the difference of the convex part of the potential. You have to pay the same guide before, but now we have extra terms that comes from the presence of the nonlinear diffusion. And I want to show you how we manage to control these 3 guides by focusing on this symmetric one, where you don't have much choice. The estimate that you can do are exactly what you do. So how to control the green term? First, we realize saying this is A plus B minus A minus B. So Okay, we dominate simply by the sum and the difference, and we put the modules inside. Okay, and now we have, okay, this guy is in L infinity. We have three terms, so you play with older with 3 exponents, but you only know that the gradient is in L2, so this is 4 to be in L2, and then you share L4 over phi and over this gradient. So you have the L4 norm of the gradient of phi. And here is where the dimension becomes important, because we have Lattice-Lenskaya inequality in 2 dimensions that is able to control the L4 norm of the gradient with the L2 norm of the function times the H1 norm of u with good exponent, 1/2 and 1/2. And also we use the interpolation of L4 between H-1 and H1. Remember that you have the whole norm, but in our case, since you have 0 mean, norm in H1 just means L2 norm of the gradient. Okay, you have these guys, and if you change the dimension, the exponents here are changing, and you see now what happens if you change the exponent. So the green term, if you use this, this inequality, the Lattice-Lenskaya to control the gradient and the interpolation to control the L4 norm there, you take together similar terms and you sum the exponent, you end up with something like this. You have the gradient, L2 norm of the gradient with this exponent, 7/4. We have this guy that is essentially the function that we have under the derivative with the power 1/4. And then you have a function here in front, okay? And now you use Young inequality to reconstruct here your function, the function that you have in the Gromov-like inequality. This is 1/4, so you have to run a power 8 to reach power 2 here. So you have 8/7 in the second, and this is a kind of magic telling you that you can, okay, finally absorb, here you have a 2, so you can absorb with the Young this guy in the red term, and you end up with your function that now, okay, this is not a constant, but this is a function. Oh, this is phi1 norm in H2 power 4. So we know that this yellow guy is integrable. It is in L1 over your time interval. And so you can conclude by simply applying your standard Gromov lemma. And this is why this extra integrability, so little extra integrability, is able to give you uniqueness. So to close this part, in the 2D well-posedness theory, the philosophy is the following. In 2 dimensions, this improved regularity that we can show also to be true in 3 dimensions. But here, because of the dimension, is exactly the gateway. It is the key to control the nonlinear diffusion term and obtain first uniqueness of weak solutions, as I showed you, just a little tip. Propagate higher regularity on positive time interval, and this requires a lot of work, but we can do it relying on the yellow new estimate. And then once you have the smooth improving strict separation and the energy equality, let's say we have a standard Caniglia stuff to run this. But this is not the end of the story, because of course I'm cheating here. The presence of the variable mobility there at B of phi in the first equation strongly affects the picture I'm describing, even when the diffusion A is constant, okay? And we developed fundamental tools to handle non-degenerate mobility with the colleagues Pietro Galimberti, Stefania Gatti, and Andrea Giorgini in a previous paper on JD that is devoted to studying the Caniglia equation, the classical one with the A constant, but with non-degenerate mobility. And you see that it's much more complicated. We have to develop a machinery that is able to control also the B part of the equation. And in this paper, you find the extra tools necessary to deal with the nonlinear diffusion. This is the 2D well-posedness theory, and let me run to the long-time behavior of our system in 2 dimensions. This is the result. We are able to prove convergence to equilibrium. When A is analytic, the nonlinear diffusion term is analytic, and this is M once again, this is B, is C2. Each trajectory stabilizes towards a single equilibrium as time goes to infinity. This means that for every initial datum, there exists a unique phi infinity in SM. I show you immediately what is SM, such that the whole trajectory, this is not up to subsequences, the whole trajectory runs through towards phi infinity in a strong norm, strongly in H2. Phi naught is a stationary state of the energy. It is a critical point. It is an equilibrium. What are equilibria in this setting? Here is the class S of our equilibria functions in H2 with potential in L2 that solves the elliptic system or quasi-linear elliptic system, but uniform elliptic system that you see here in equation 1. Of course, the mass has to be conserved. This is why you don't see here 0 as it is classical, but you see a constant, and you can also compute explicitly the constants once you have a solution. So it is fundamental to prove this theorem, to study this set of equilibria, but not only, because the strategy that you typically follow when you have a gradient flow and you want to study the asymptotic behavior, you have a strategy in 3 points. You have to rely on some pre-compactness of trajectories to identify an omega limit as t goes to infinity. And this is done by smoothing. We have enough information. You have to identify the omega limit set with the set of equilibrium stationary points. And essentially we have. And then what it is needed is a celebrated tool very used when you have to prove convergence also in machine learning of finite dimensional stuff that you use. Okay, this celebrated and well-known tool to exclude, in this case, continuum of limit points when t runs to infinity, and to obtain convergence to a single equilibrium. This is the celebrated Lojasiewicz-Simon inequality that goes back to 63 in the finite dimensional case, and then was extended to first cases of infinite dimensional space by Simon in 83 for analytic energies. Okay, for the classical Canhilliard energy with a constant, the Simon-Lojasiewicz is well known, goes back to the works of Hoffman and Rippern and refinement by Abels and Wilken, as I showed you before. But what happens when A depends on phi? The Simon-Lojasiewicz was not known, and we tried to show a suitable version, to prove in this paper a suitable version of the inequality. And this is the result. We are both in 2 and 3 dimensions. We assume that A is real analytic on the open interval because we need to extend it. This is our energy, and this is the inequality. So we choose a stationary state of the energy with this extra regularity, but in a while we tell you that this is not extra at all. Every critical point of the energy has this extra regularity. Then there exists a certain exponent, gamma here, between 0 and 1/2, and 1/2 would be the optimal, in fact, such that the gradient, essentially, of your energy is able to control the difference, the gap in the energy from the level of your critical point and the energetic level of an extra point that is close to our critical point. Okay, here this is not the plane gradient, this is the gradient with the constraint of having fixed mass, and this is why here it happens that you have the line over, this is the mean of the gradient. And if you write it explicitly, this is exactly the guy that you have on the right-hand side. It represents essentially the norm, the L2 norm of the gradient. In which space we are working, we are working with a little extra regularity with respect to the energy space, but this is not a problem because we use this object here on smooth branches of solution. We already have regularization, so we are working in H2 with Neumann boundary condition, and we are close in the H2 norm, sufficiently close to the critical point. Of course, in the space where you are conserved with the same total mass that is. And with this analytic tool that is inspiring the proof by this nice work of Fabian Rupp, we can also run a 3D theory, something about the 3D theory, just a few minutes to tell this, that is developed in this paper. And 3D, we are much less lucky because, okay, this is a philosophy. What we can show, that weak solutions exist, we already know, and we can improve the regularity I used before. But of course, in 3 dimensions, this is not enough to prove uniqueness, not even in higher regularity for weak solution. Just to tell you, this is exactly the picture that you have with the canonical equation, just with mobility and a nonlinear diffusion that is constant. So this is not essentially the best that you can find in the literature. with no hope to prove uniqueness and smoothing in 3-dimensional. But then we focus on strong solutions. So we assume that the initial datum is a bit more regular. So it is in H2, and with this guy here, that is essentially the initial chemical potential bounded in H1 by a certain constant, this big M here. Well, we can prove that strong solutions exist, but just locally in time with a measure of M that we can explicitly compute. Unfortunately, it just depends not on the single specific initial datum, but on this constant big M here. So we have locally in time strong solutions. We cannot attach uniqueness, but maybe we can say that some local solution becomes global in time. We try to do this. And in light of the Simon-Lojasiewicz inequality I showed you, we are able to prove that for well-cooked initial data, global in time, the strong solution becomes global in time. And this is the result that we call Lyapunov stability for A analytic and B of class C2. Take any local energy minimizer of your energy in the energy space, and assume that the initial datum in W satisfy assumption M that I showed you before. So the assumption for running a local in time strong solution. Then for any epsilon, there exists a constant depending only on epsilon and M, such that if your initial datum is close enough within eta in the H2 norm to the local energy minimizer, then the unique strong solution becomes global in time and remains close within epsilon to your energy minimizer. And now that you have the global solution, you can run, as in the 2D case, the Lojasiewicz-Simon stuff to prove also the convergence to a single equilibrium. Okay, final remarks about this. The new Lojasiewicz-Simon inequality is the key because it ensures that the energy cannot drop too much to leave the neighborhood of the local minimum. So the Tm that you find for the local solution remains the same, and you can patch your local solution starting from subsequent initial datum. So essentially, your local strong solution can be extended step by step on time interval of the same length, thanks to the uniform control that we have with respect to M, and with the crucial role of the Lojasiewicz-Simon inequality and of the energy inequality to control the gap in the energy. As I told you, we can prove the convergence to a single stationary state in 3D for strong solution, but this result has been already improved in this work by Grasselli and Pogliotti, where they are able to prove, relying on our Simon-Lojasiewicz inequality, convergence to equilibrium in every space HS for any weak solution in the 3-dimensional space. So with this, I think that I can conclude just telling you that understanding the mathematical properties of the Canadian equation, even in its simplest form, is essential for many modern PDEs because the Canadian equation nowadays is a fundamental component of many much more complicated physics models that are used coupled with other physical mechanisms to do much closer to reality modeling of, for instance, tumor growth, tissue evolution, crystal growth, and stuff like this. And with this, I thank you very much for your attention.
Okay. Thank you very much, Professor Monica Conti, for the very nice presentation.
Thank you.
Then at this moment, we have some room for the questions. So to the participants, please remember that you can write.
Okay.
Please
Please tell me.
remember that you can write questions on the chat by YouTube or in the Zoom platform. If someone wants to make a question to Professor Monica Conti, just please go ahead, just unmute yourself and make your question. I don't know, for instance, if Jenny has a question. Yes?
Yes, I have a question. So thanks, Monica, for the beautiful talk. It was very clear. So just a curiosity, in one of the paper, you wrote that the mobility is non-degenerate.
Yes.
Right?
For us, non-degenerate means that it cannot touch 0. Okay, so it remains
But-
this essentially means that when you have the integral estimate of the mobility times the gradient, you indeed are estimating the gradient. Okay, so it is reconstructing the full norm of the gradient. Otherwise, we are in trouble. Studying the Canadian equation with degenerate mobility is a problem. We have few results just concerning the pure existence of weak solutions. We are studying the problem with, but it is quite tough. And just hoping to
imagine. Okay, thanks.
Thank you, Jenny.
Very good. Thank you to Jenny for the question. Is there are more questions from someone from the Zoom platform, maybe from the Zoom room for Professor Monica Conti, Professor Susana Terracini? Do you have a question?
No, not at this moment.
Not at the moment. Okay.
I enjoyed very much the presentation,
Thank you, Susanna.
which was very, very clear.
We were
Maybe
very
you
happy.
recognize the picture in the slides.
Very good.
A great inspiration for me.
It's very interesting. In the chat, Marcial says thanks a lot, Professor Monica. And then now the question says, what about the case of cured surfaces? I just defend my thesis in numerical methods of PD on surfaces.
The research is very active also there. There are results from Pogliatti and the German school of the cannular on surfaces. And okay, the works are, the papers are quite complicated from a technical point of view, but from the point of view of, okay, philosophy, when you have a surface, essentially, most of the computations becomes two-dimensional. So indeed, you can hope to prove more and to have the complete picture as in our 2D case. So there are many references that I can give you about the evolution of the cannular on surfaces, running surfaces.
Okay.
Very technical and sophisticated topic, but from the point of view of philosophy, most of the stuff reduces to a complicated form of 2D formulation. So you have the hope to have the complete picture.
Very good. So it seems also that Marcial is very interested in following the activity between your team. So probably he will write you later.
Write you an email and we will.
Yeah. So Marcial, please feel free to write to Professor Monica Conti to express other questions. Very good. So I personally have also a question, right? And especially because, for instance, Jenny works in control theory and also myself I'm interested in that topic. Have you considered the case of the problem about the controllability for your model?
Not personally, but of course it is of interest, and there is a huge literature about control with cost functional, and especially for models involving tumor growth, so medicine and control mechanism in the model, so in more complicated pictures. So there is a lot of literature. If you wanna, there is the school by Pavia with Spreckels, Gilardi, Colli, Andrea Signori, that are very expert of this, and a lot has been done in more complicated models. So for the basic candidate, certainly it is there. For with the presence of nonlinear diffusion, I don't know, because differentiability of your cost functional is important, and I don't know what happens when A is involved. This might be quite sophisticated to be checked. But there are many people telling you that there is a machinery that we can run to reach control in presence of the cannular modulus as a part of your big system.
Okay, thank you very much. And maybe another question, right? Because, okay, you have the Laplacian in your Hilliard equation, right? But I wonder if, is there a fractional analog for this model using instead of the Laplacian, the fractional Laplacian?
I'm not an expert, but the research is active also in that stuff. I'm really not an expert. I
Okay.
cannot tell you what can be done and what not, but I can give you references about this.
Thank you very much.
My pleasure.
Okay, so then thank you very much to Professor Monica Conti for the very nice presentation. Then now I pass the word to my colleague, Professor Jenny Fragnelli, who will be the chair of Professor Susanna Terracini.
Okay, thank you, Duvan.
Hi, Jenny. Hi, Duvan.
Ciao.
Can you hear me well?
Yes, could you try to share your slide, please?
I'm going to share my slides. Okay. Oh, wait. Can you says that I'm not allowed. Okay. Maybe now I am.
Yeah.
Okay. So let me do. Okay. So here you can
Okay.
see my slide and I put.
Yes.
Okay. So
Okay,
now
so
you can see
yes,
in the
we
full
can
screen
see.
mode.
Yes. Okay, so it's my pleasure to introduce Susanna Terracini. Susanna is one of the most famous Italian mathematicians in the world. She works in Hamiltonian dynamical system, including the n-body problem, reaction diffusion system, Schrödinger equation. Her dissertation was supervised by Ekeland and Sulimini. She was also the supervisor of Monica Conti. She is author of about 150 papers with about 4,000 citations. Actually, she's a full professor at Turin, and as of February 2026, she's a member of the Scientific Advisor Board of the Barcelona Centre de Ricerca Matematica. She has received several awards for her work, including the prestigious Schauder Medal from the Schauder Center for Nonlinear Studies at the Nicolaus Copernicus University in Turin. In 2007, she won the Bruno Finzi Prize of the Istituto Lombardo Accademia di Scienze e Lettere. She has also secured substantial research funding, including a grant from the European Research Council under the European Union's Horizon 2020 program and the national research projects from the Italian government. So today she will speak on singularly perturbed elliptic system modeling, partial separation, and their free boundaries. Please, Susanna, thank you very much.
Thank you. So first, I would like to thank heartedly the organizers for giving me the opportunity of being here today. My family, the father's family, has spent several years in Argentina during escaping from the racial laws, discriminative racial laws in Italy from 1939 on. And so a piece of the heart of my father, but also of us, is in Latin America and especially in Argentina. And we are all big fans of Argentina as a soccer team. So now coming to mathematics, what I'm going to share with you today is a talk with let's say, historical account of 20 years of research about segregation driven by competition. And then I will introduce some new aspects, some new problems related to what we call partial segregation problems. So this topic is very, very much related with Monica Conti's talk, but with some big difference. Again, there are some region, some energy, and there is some pattern formation. But here the situation is a bit different because there are two two elements. The first one is diffusion, and the second one is separation that may be modeled in different ways. The number of competing species can be whatever. And the energy involved, contrary to the Cannes-Billiard case, do not contain terms which accounts for the area of the limiting interface. So there are only two elements, so it's kind of a less structured problem. And there are also different variants of it. So, and especially when the competition becomes extreme, the competing species segregate. This means that they occupy different regions of the space. So they produce this way some free boundary. So this is PDE with some parameters and a singular limit, which is basically a free boundary problem. In this paper, in this seminar, we will first examine the case of total segregation and then that of partial segregation. Oh, okay. So let me start with the equations. We will consider a time-independent case, so stationary case, but you can also think that the operators are time-dependent diffusion operators. Okay, so maybe time-dependent or time-independent. Then we have some terms which takes in account of the self-interaction of the density of the population within itself, and then we have an interaction with the other components, and this interaction is of competitive type. This means that parameter beta, which is a scalar parameter, and functions gi are both positive, and so this term opposes the diffusion. The self-interaction may, in some problems, oppose, in some other problem, help, or focus or defocus the problem, but we can just think that it's zero because it will play basically no role in what I'm going to talk. There are two very, very popular models in type of interaction. The first is quadratic in the sense that is a polynomial which is the sum of quadratic monomials. This is very popular in population dynamics, like in Lotka-Volterra system with diffusions, may have symmetric or asymmetric interaction, and in general has no variational structure. Then it's also of huge interest the case of cubic interaction. Again, we have a polynomial or a degree 2 homogeneous polynomial where the interactions are some of this type, and this may have a variational structure and arises in quantum mechanics in partition problems, and also, as we will see, in the field of harmonic maps into singular target. Okay, so to start with, we consider a domain. We have a number of species. We just drop all the unnecessary terms of the equation. And we may fix, just to avoid trivialities, some boundary data, and which are already segregated. And then we will try to let the parameter beta, which models, by the way, with respect to the previous slides, there is the minus sign on both sides has been cancelled. cancelled out. Okay, so what can we say of such a type of system? Well, first, for given boundary data, there is a minimizer, and also this minimizer is uniformly bounded with respect to beta. Okay, so if we let beta go to infinity, we will have that the energy, the Lagrangian energy, will stay bounded, and also the potential, the total potential, which is the sum of these quartic monomials with a beta in front, will stay bounded. So if we pass to a weak limit, we find something which is a configuration which is segregated. This means that the products ui and UG times uj are pointwise almost everywhere 0 if I is different from j. Okay, so for example, we can play this game and then look at this limit and ask ourselves some natural questions. Whether U is a minimizer or even the minimizer of a limit problem, whether the convergence can be improved going from weak H1 into something more strong, and what is the possibly optimal regularity of the limit densities, and what is the geometry of the emerging free boundaries. Okay, and let's say in the last 24 years, there has been a very rich literature about, and now we are able to give a rather exhaustive picture of the problem. With this, we mean that the approximating densities when beta is finite are uniformly bounded in C0 alpha for every alpha locally, but also globally if we wish to if we extend in a reasonable way to the boundary. And there is convergence for subsequences, so there is compactness in such elder spaces. In particular, the limit profile are continuous for C0 alpha for every alpha, and in particular, one can prove that they are Lipschitz. One can even prove the presence of Lipschitz bounds uniform in beta, and this is in any case the optimal regularity for the limiting profile. Okay, what does the limiting profile do? It will minimize the sum of the energies with a point-one constraint of being segregated. Okay, if you want to see this as a harmonic map problem, the singular target in this case is just the union of the coordinate axes in Rk, where k is the number of components. Okay, so in this theory has been developed by many authors, starting from the very pioneering works of the Dancer School. Then we also with Monica, in a team with Monica and Gianmaria Verzini, we studied especially the variational approach, but also the asymptotics with respect to the competition parameter. There was then a very enlightening paper by Caffarelli and Lin, who did apply the free boundary approach to the problem, and also related with other works by Bozornia, Ven and Velichkov. The variational theory was developed with special notions of extremality, because you see that in the limit, in the segregated limit, there are no differential equations. There are differential equations, but also free boundaries, and it's important to give the transmission condition to devise the transmission condition at the boundary. These problems are very much related with the problems of optimal partitions related to linear and nonlinear eigenvalues. And finally, there were extension to fractional, non-local, asymmetric, and there's anisotropic case. Okay. Now, this is very roughly a picture of what happens in the case of total segregation. So this means that two components that at a single point of your domain, there can be only one component, one species which is non-zero. But as we will see, when we allow more than one species to be different from zero, we find not only a variant of the total segregation, no, it's not just a variant, it has to be developed with a different viewpoint, even though in the end you will see results are not so different in nature. Okay, so let me spend one more word about the total segregation case. So in each domain, on each of the supports, the components, the species are harmonic, the densities are harmonics, and then, as I said, the product of two different components is always zero. There is an important element because we have to add to this system also something that encodes the interaction of two or even more species, densities at a boundary set of its positivity set. So we have a free boundary, which is the set, the union of the borders of the positivity set, and we also have a nodal set, which in principle could be different. Okay, but it happens that there is not zero. They are in fact the same set, and this local Pozaev identity encodes the transmission, the interaction, the validity of this in every ball of the domain. And the final result is that the free boundary is a collection of smooth hypersurfaces up to a singular set of Hausdorff dimension at most n-2. Okay, so the philosophy for the total segregation is as follows. We have strong competition that forces a pairwise exclusion. Then we have this local Pozaev identity that provides a monotonicity formula, and also the Alt-Caffarelli-Friedman monotonicity formula plays an important role here. And these monotonicity formulas give compactness and blow up limits. And then we find that at the regular points of the interface, we have a reflection law, and the reflection law is also encoded in the validity of the Pozaev, local Pozaev identity, so we can call it a weak reflection law. And what is also important is to notice that the features of the nodal set of the free boundary is the same as that of the nodal set of solutions to elliptic or Schrödinger equation. Okay, and as I said, this philosophy has been applied, and the results have been obtained also for rather different variants of this problem. For example, the diffusion by the local Laplacian can be replaced by that of the fractional Laplacian. We may have a competition at a distance, which is this is a very interesting and funny problem. We may have anisotropic systems where the diffusion is different, has a different nature depending on the particular species, but all these type of interaction yield total segregation. Okay, so the total segregation means forbids pairwise coexistence, but there are situations where it's natural to think that some of the components can be non-zero at the same point. So we can try by replacing this constraint. Okay, ui times uj is equal to 0 almost everywhere if I is different from j, with the constraint that the triplet, let's assume that we have three components, that the whole triplet u1 times u2 times u3 is equal to 0. So this means that at each point there might be two densities which are non-zero, but one has to be 0. Okay, so from the point of view of harmonic maps, total segregation leads to harmonic maps into the union of coordinate axes. One proves Lipschitz regularity, and then we have interfaces between phases. When in the case of partial segregation, we have at most two components positive at each point, and this, as we will see, leads to a problem of harmonic maps. If we look at the corresponding energy minimizing problem into coordinate hyperplane rather than axis. And as I am spoiling a bit, this will not give Lipschitz regularity, but C0 3/4 regularity. And here, also the notion of interface has to be changed, because will not be the interface, merely the interface between two phases, but is the interface between coexistence regimes. Okay, so this is kind of new paradigm and not merely a new interaction term. Okay, let me just spend two words about motivations. Okay, one motivation can come from mean field equations and energies like Gross-Pitaevsky for mixtures of Bose-Einstein condensates. Okay, let's look at this energy. We have let's say a Lagrangian energy for the components. Then we have an interspecies energy, which will be this one, which accounts for interaction of the atoms of the species with itself. Then we have the interspecies, the two-body interspecies term, which is something that accounts for binary interactions, binary collisions of atoms. And then you may add an account that a term that accounts for ternary interactions. So ternary collisions, collisions of atoms of the three different species. Now, of course, if this coefficient is large with respect to the other, we can somehow neglect this term and just look at the energy, which is the sum of these two terms. And this has been, well, let's say, of course, not the limit, but there are cases where, in fact, this coefficient, which is called, which is one of the scattering length, is very large with respect to the other. But maybe I like more another point of view, which is actually an analogy rather than an application, even though it could also be an application. And assume that we have a metric graph, and we wish to give a label among three possibility to each node of the graph. Okay, so this means that we know, so for example, let's say that the three labels correspond to colors: red, yellow, and blue. Okay, and these are in fact the three elements of the standard basis of R3. Okay, now this is called semi-supervised learning process. Consists in considering the Dirichlet energy of the graph. Okay, then we have some labels which are some vertices which are already labeled, which are in fact correspond to our boundary. And then we may have the choice. For example, we can think that each node has at most one label, one color which is active. And then we add this penalization term to the energy, and we have the diffusion which is associated to the graph energy, which is opposed by this, which is more or less a penalization that eventually will lead to this constraint. Okay, so the idea is that colors diffuse through the graph with this penalization. And when beta goes to infinity, we have only one, at most, one label different from zero at every node. Okay, now let's see what happens when we add this other type of penalization term that will lead, when beta goes to infinity, to the constraint that the product of U1, U2, U3 is equal to 0. Then again, there is a mechanism of diffusion which is opposed by this penalization when beta is very large, and at each node we will have at most two colors which are active. And then you can play, okay, with some example, with some graph, and then what happens is that for the hard partition, you will have a red, a blue, and a yellow zone in the limit, and a free boundary. In the second case, you may allow two colors to be non-zero at each point, and then so you see the presence also of mixed colors, so green, orange, and violet, and eventually there is also a nodal point, a point where no color is active, but this will reduce to a single point. So the free boundary must be somehow rethought from a different point of view. Okay, so now let's go to our partial segregation problem. We have a domain, let's simplify things, and we have three components, three species, and we consider the problem where the Laplacian is equal to beta, these terms, okay? Okay, what is this? Is actually, if you multiply both sides by ui, you have that ui times Laplacian of ui is equal ui square, u2 square, u3 square. Okay, so this is just. And if you look at the associated energy, this is the sum of the energies of the plus the beta times the product of the square of the three components. Okay. Now, again, the existence of a minimizer is not a problem, and the boundedness of the energies of the two terms of the energy also is not a problem if the boundary data are properly chosen. And then when beta goes to infinity, you find again a weak limit, which is a weak limit in H1, which is partially segregated. Okay, so now the first question again is to wonder whether this asymptotic, when beta goes to infinity, can be made stronger with respect to the function space. So go from H1 log to something stronger. Okay, and okay, so the first result that which these are recent results obtained in collaboration with Nicola Soave, is are Elder bounds for small exponent, which is in a first result is not known. I will come back to the optimal one in a moment. And so the first theorem is about uniform bounds, local bounds in Elder space for a small exponent. So this is enough to, well, first to pass from weak to strong convergence, and also for saying that the minimizer itself will be Elder continuous. And then this is already a nice advancement that the positivity sets are open set. Okay, again, the limiting problem has also a variational formulation, and one can prove that this limit profile minimizes the sum of the energies with the same boundary condition with this constraint. Okay, the constraint that u1 times u2 times u3 is equal to 0. Assume for a moment that everything is positive. Okay, and then again we have harmonic maps into some singular target, but this target is not anymore the union of the coordinate axis, but is the union of the union of the octant, of the positive coordinate octant, and as such they are stratified as a geometrical object. We have two-dimensional faces when one of the coordinate is 0, one-dimensional straight line where two are zero, and there is also a zero-dimensional point, okay? And what is interesting, if one look at the geometry of the target, is that, well, of course, this is a singular, though stratified object. It is not geodesically convex. Okay, this is a big difference with respect to the full segregation case. And as such, okay, this is for those who know about the harmonic maps, the theory of harmonic maps into stratified targets. The length of the normalized boundary of the set of the link, sorry, is 3 pi over 2, which is strictly less than 2 pi, and this means that this target does not fall into the regularity theory of harmonic maps, which was developed before in the by Korevar-Schoen, Gromov-Schoen, Yields and Fuglede, Daskalopoulos and Mese. So also from this point of view, we are in a not exactly standard case, even though some of the technique that we will employ are very similar. Okay, so the first theorem was about the bounds in spaces of order continuous function. The second result is about the regularity of the free boundary. Okay, so first, what is the free boundary? Well, in fact, you could have different ways of defining, but let us just consider, but they are all equivalent, and it is just the union of the boundaries of the positivity sets of the components. Okay, so it could be also defined as the set where at least two components vanish at the same time. Anyway, it is the same. And this has Hausdorff dimension n minus 1, can be written as the union of two sets. The set, what we call the regular set, which is the union of smooth hypersurfaces of dimension n minus 1, and a singular set, which has Hausdorff dimension at most n minus 2, and is a discrete set in dimension 2. Okay, and this is, if you look, exactly the same result. Okay, but here the notion of free boundary is different. The definition of free boundary is different for the total segregation case. Okay, now again, we have some initial similarities. We have the validity of Laplace equation in each set of positivity, which are open, positivity set. We have that the product of the three component is always 0. And then again, we have the validity, where this follows from the validity of a similar penalized identity. We have the validity of the same Pos-IF identity that we had before. And this may be used as an alternative definition of extremal configuration. And again, the interaction among two components is actually encoded in this local Pos-IF identity. Okay, let me give two examples. Okay, four examples actually. No, three examples. One is an example in 1D. Why not? And then we have one component is constant, and the other two form a two-plane solution with the same slope. But also we may have something different. We may have that one component is a one plane, okay, and the other two are also two planes, okay, with a slope which is not 1 anymore, but is 1 over square root of 2. Okay, and then if we go to the disk, we find as extremal configuration, examples of extremal configuration, something like this. Okay, so the positivity set of each component is the intersection with a cone of angle 4 pi over 3. So you see that these overlap 2 by 2 on the whole disk. And so the free boundary is actually the union of these three segments. Okay, and because of this example, we imagine that the optimal regularity should be C0 3 over 4 and not Lipschitz, because conic functions on angles which are larger than pi are not Lipschitz, are only Hölder. Okay, now let me spend a few words about some ingredients of the proof. First, if we wish to prove uniform bounds with respect to beta, one can argue by contradiction and blow up and construct blow up sequences which will have a limit. Okay, and this limit may fall in different classes. So one is this one, for example. We have that the limit is something where the Laplacian is 0, and these are where the components are positive, and again they are partially segregated. But also, or we may find some limiting problem when the solution will solve this equation, this system of three equations, which is similar to the beta problem. And well, for extracting some information from that, then we can try to extend the Alt-Caffarelli-Friedman monotonicity formula to this case. And we consider this weighted geometric average, geometric in the sense that is the product of three averages, three averaged energies, and one find that this for a suitable choice of this exponent nu is a monotone non-decreasing as a function of R, and this helps in proving some Liouville type theorem that prevent the existence of non-trivial segregated states, partially segregated states as before. Okay, so this is interesting, and it's interesting in itself because this exponent nu can be characterized in terms of a spectral partition problem of the sphere. So now you take the sphere, you take three sets on the sphere with the property that three open sets on the sphere with the property that if you take the intersection of all three, this is zero or has zero measure. Okay, and then you consider the the characteristic exponent, and you sum these, and then you optimize with respect to all possible such partition. Okay, and now we understand that this is not yet the right way of obtaining the optimal exponent, even though it's good enough to obtain something, some initial regularity, Hölder regularity, because for this problem, the best partition is to eliminate one of the three. So one of the three will have, no, sorry, not eliminate, that one of the three components will be just the whole sphere, and the other two are contending the rest of the sphere, the sphere, so dividing in two half sphere. And this is more convenient energetically than this other configuration. So this is already something, but is not yet the optimal one. Okay, now now we have an initial Hölder continuity, and we work with the regularity of the free boundary. Okay, and as I said before, there are different ways of defining the free boundary that turn out to be all equivalent in our case. And this is, for example, the union of the boundaries of the positivity set is fine. Okay. And then there are some let's say, observation, which are rather elementary somehow, as if one component is identically zero, then the constraint is fulfilled everywhere. And then the other components either are identically zero or they are never zero in a ball. If two of the components fulfill the constraint already, then the third is harmonic. And also, if you have one component which is non-zero and the other one may alternate their positivity or not, then the difference of these two is harmonic. Okay. And then one can also add a new element, which is the Almgren monotonicity formula, which is related, which is a, let's say, classical tool in regularity of harmonic mapping. But this time it's a bit the monotonicity is a bit more complicated. Anyway, this Almgren monotonicity formula will give the existence of homogeneous blow-ups at triple points, and with this we can prove our regularity theorem. Okay, a regularity for the free boundary. Just a remark that in fact here we need not only extremality, but we need the full minimality of the configuration. And then as a last result, we obtained the optimal exponent, Hölder exponent for the elements of the minimizing family. And so the limit function R C0 3/4. And in 2 dimension, we also have a kind of Taylor expansion close to any triple point. As I said before, triple points in 2 dimensions are isolated, and this will be the expansion. Okay, so let me just conclude, because my time is over. that the partial segregation indeed changes the geometry of exclusion. In this case, the phases exclude each other pairways, as I said, and coexistence is allowed, but only up to a certain number. So if we assume to extend our result to k component that compete that can be non-zero L by L. Again, we find a limiting problem related to some singular target which is non-convex and do not belong to the known classes of for the standard regularity theory. And the optimal exponent here becomes 3 over 4, and for more general problems, it's not 3 over 4, but is always less than 1. Okay, so this there are new developments by Soave, by Giarretto and Soave for let's say extending from triple interaction to more general interactions. And I think that my time is over. So thanks for your attention.
Thank you very much, Susanna, for your nice and clear talk. So are there some questions? You can write in the chat and then I can read to Susanna. So I can ask you something waiting for other questions. So just a curiosity, Susanna. So you assume that beta is strictly greater than 1. This is related to the fact that we want beta large, or we can assume, for example, that beta is also strictly less than 1.
No, okay. What I have, this talk was concerned with the singular limit when beta goes to infinity. Okay. When beta
Okay,
is
so
small, this means that there is a balance between the diffusion, or maybe also the non-linear self-interactions of the population and the competition. Just to simplify and to look what is the limiting configuration when beta goes to infinity. I just dropped all the other elements and that form altogether the model.
Okay, and another question, can we improve this 3 over 4 adding some assumption, or no?
No, in this case, 3 over 4 is the best. If you wish to improve and not to have something singular, you must change rather drastically the model. You should not allow the interaction to be a pure ternary one. Okay, so this is
this is the best one. So in the chat there is a question. So is possible to replace the penalty approach for segregation to some kind of augmenting Lagrangian formulation?
Sorry, I don't really understand very well the.
Perhaps you can read directly in the chat. I don't know.
Okay, let me just show. Okay, here we can find the energy I am. Okay, yeah. So I don't know if I got the point. You have mainly somehow two possible point of view. Either you add this penalization and let beta go to infinity, okay, or you have a pointwise constraint. So you consider a constrained Lagrangian, okay, with pointwise constraint with respect to U. And the constraint, as I said, is not really neither convex nor smooth stuff. And one of the results is that the second problem is in fact the limit of the family of these the minimizers of this penalized functional. Maybe I didn't get the point, but
I don't know. I think yes. It's are there some other questions or remarks? So there are other comments, other people that thank Susanna for the excellent talk.
thank
But
you.
there are no other questions. So if not, thanks again, Susanna, to accept our
Thank you.
invitation.
Thank you for your attention. See you soon, hopefully.
I hope.
Thank you very much.
Bye.
Bye.
Anna.
Bye.
Bye
Bye.
bye.
So now there is Barbara Kaltenbacher.
Yes. Thank you, Jenny. Hello.
Hi, Karin.
Hello, everyone. Yes, our next speaker is the Professor Barbara. We have for that 8 minutes to
Yes.
start with the next talk. So, okay, we will wait.
Yeah, Barbara is not yet in the
Yeah.
meeting.
Yes, exactly.
So we wait for 8 minutes.
Yes. Okay. Okay, so we have a slight delay, so maybe we need to wait a few minutes more, okay? And we will continue. We will continue soon. Thank you.
Professor Barbara Cantelbenga, can you hear me?
Professor Barbara? Okay.
You have, Professor Barbara, you have now the permission to unmute yourself and of open your video.
I think the Professor Barbara lost the connection.
Okay.
Yes.
So she will return soon.
Yes. Yeah. She came back. Hello, Professor. I can see you, but I cannot hear you. Let me check. Okay, please, technical support can be, do the Professor Barbara co-host? One second, Professor. Okay, now you can unmute yourself.
Okay, here we go.
Good,
Finally.
great.
Sorry, it was yes, I was
No,
not
it's
prepared
okay.
to having to be okay.
It's okay, Professor. Great, you are here with us.
Mhm.
Thank you so much for accepting our invitation.
Thank you. Thanks a lot for having me.
Thank you.
Mhm.
Professor, maybe could you try to share your screen?
Yes.
Thank you. Great. I can see your screen now.
Yes, I'm trying to do full screen. Here we go.
Mhm.
Okay.
Excellent.
Okay.
Could you try to pass the slides just to check everything
Yes.
is working well? Great.
Yes, it
Okay.
seems to be okay.
Okay, thank you. Okay, so we will continue with the scientific program. I am very happy to be here with you today, Professor. It's a great honor to introduce the Professor Barbara Cantelbacher. I am not sure if the pronunciation is okay.
It's okay. It's perfectly fine.
Well, thank you. The professor is from the University of Klagenfurt in Austria. She is a highly respected mathematician, recognized internationally for her outstanding work in applied mathematics, particularly in the field of inverse problems and PD constraints optimization. Beyond her excellent research, the professor is a dedicated leader in the mathematical community and has served as the president of the Austrian Mathematical Society. We are thrilled to have her with us today. So the time is your, Professor. Thank you.
Thank you. Thank you for your kind introduction. And sorry for the technical difficulties, which probably anyone else would not have. It's just always me who struggles with these things. Sorry for that. Okay, I hope you can see my screen. Can you also see my pointer?
Yes, I can
Yes,
see
okay,
the
that's good.
pointer.
So that because so they can point to things. Okay, the topic that I would like to talk about today is about an inverse problem of identifying space-dependent coefficients in a certain PDE that plays a role, a crucial role in MRI, magnetic resonance imaging. And so I will start by just introducing the model because it's probably not very well known, this PDE. Say a little bit about the analysis of the forward problem, and then I would like to mainly spend time on showing two uniqueness results for the inverse problem. So it's always for inverse problems, it's always important to prove that yes, the observations that one has uniquely determine the searched for quantities and or in which sense they uniquely determine them. And depending on how much time there is, I might just have one of the two approaches that I can show here. Okay, so this work has been done in the framework of a collaborative research program that has recently started with colleagues in Graz and Vienna here in Austria. It's about the title is Mathematics of Reconstruction in Dynamically and Active Models. So with this we mean evolutionary PDEs modeling some kind of imaging, and we want to reconstruct images from indirect observations. And active means that at some point we will also want to go ahead and control the input in such a way that the reconstruction is optimized. But that's not yet the topic. And what I'm going to talk about today is contained in a paper that is to appear in Mathematical Models and Methods in the Applied Sciences. So here's already on one slide the whole problem. So of course you are not supposed to look into everything at once, but that's actually the, well, sort of monster that we are going to deal with, the so-called Bloch-Torrey PDE. And in fact, it's a convective version because we also have a velocity term here. That's the PDE, that's the model, and that's the observations that we have. And I will try to explain a little bit about what all these things mean. And well, some of you might have heard about magnetic resonance imaging as a mathematical problem already. Usually it's viewed as doing some sparse sampling of the Fourier transform, namely spatial Fourier transform, and then inverting this sparse sample for a coefficient, for example, for this equilibrium magnetization. But in fact, as we will also see later in this talk, this sort of inversion of Fourier transform relies on simplifications of the model, and it relies on very, very specific excitation. So excitation is in fact contained in this B1 here, very specific excitations that allow to make these simplifications, but they limit the data acquisition process in the sense that after having done one excitation, one always has to wait until basically everything has returned to equilibrium. And that's in fact the reason why MRI acquisition takes such a long time. And so our goal is to do it model-based, so not do the simplifications, but then we have to look at the full model, and but using dedicated sequences, dedicated excitations to allow for really fast data acquisition and also content-rich data acquisition. Okay, that's more or less in one slide what we are after. Now let's look a bit into what all these terms in the model say. And for this, I would like to show you this picture of the physical background of magnetic resonance imaging. So the physical process is, of course, it's magnetic. So it's magnetics. So at the beginning, one has some ensemble of randomly oriented spins. So these are rotating objects, and many of them. And then the first step is to impose a very large magnetic field, B0, in a certain direction. So in our coordinate system, this is the Z direction, which is also called the longitudinal direction. And it's really a large magnetic field. So that's what you sometimes read of, that this device has a 1 Tesla or even 3 Tesla magnetic field. And that's really the effect of this is that all these microscopic spins basically align into one single net magnetization, where this net magnetization still also has a sort of spin direction, as it's indicated here, namely spinning now around this main axis, the longitudinal axis. And there's also something transversal to it, of course, in three-dimensional space, namely the XY plane. That's the so-called, so this is longitudinal, this is transversal. So longitudinal is in the direction of the B0 field, of the main field, and then transversally to it, it's the XY plane. That's how we put our coordinate system. And next step is to do an excitation, which is done by imposing another magnetic field. So that's B1 now pointing, for example, here in X direction. So it's in the XY plane. And the effect of this B1 field is that it turns, it really, one can imagine it like a handle. You will see this in a moment with the cross product appearing in the corresponding term. We take this handle and we turn it around, namely we turn the magnetic field into the XY plane. So that's what one typically does with a so-called 90-degree pulse. And it's obvious why it's called 90 degrees, because it switches the magnetic field by 90 degrees. There's also 180 degrees or less than 90 degrees, but this is sort of the typical thing that one starts with to understand what's going on. Okay, now it's switched down. But well, there's this large B0 field, and which makes our magnetic field vector aim to get back into this direction. And in fact, as soon as we switch off this excitation field B1, it tries to return into equilibrium position, which takes some time, and it just does not flip back immediately. It does so in such a rotating precessing manner. So we have this vector, maybe you can see my hand here. So you have this vector that precesses. First of all, it starts in the plane, and then it gets more and more to the longitudinal axis, to the z-axis. Okay, that's basically what's going on, and also how these terms in the equations, or at least some of them, can be explained. So there's, first of all, this cross product term. So first of all, it's about an evolution of the magnetization vector, which is a function of space, which is here denoted by R, like in the engineering notation or physics notation, and then T, which is time. And it's a three-dimensional vector. So it's about how this changes over time. And this is influenced, first of all, by a rotation term. So this B with an upper index 1, this comprises both B0 and B1. And it's a cross product. So that's why it's really, so the outcome of this, if you just recall your calculus lecture, the cross product of two vectors is just giving a third vector that is perpendicular to both of them. And that's what actually what you see here with this B1 handle that just takes it and turns it. That's the cross product, mathematically speaking. Okay, then you have another effect, namely of this M vector wanting to return to equilibrium position. So what is equilibrium position? So it's 0, 0 in XY direction, and it's the equilibrium magnitude in Z direction, in longitudinal direction, multiplied with these reciprocals of relaxation times. Okay, that this describes the relaxation towards equilibrium. And there's two further effects that you did not see in the previous slide, namely diffusion, which comes from interaction of spins among each other, basically. and convection, which it can come from several sources. So it can be, for example, convection inside the imaged body due to blood flow, for example, or also due to motion of patients. So we know lying in such a machine takes a while, and then at some point we might move a bit, and this also influences, of course, on how the magnetization evolves with this convection term here. Okay, now we have a better understanding of the Bloch-Torre equation. Now let's also spend a bit of time for explaining what all these quantities are here. So as already mentioned, M is the magnetization vector, and it nicely splits into this longitudinal part, the Z direction, and a transversal, actually two-dimensional transversal part. So the X and Y part together give the transversal magnetization. There's this equilibrium magnetization to which the magnetization always wants to return. There's these relaxation times, and it's depends basically on whether it's relaxation in the XY plane. This would be the spin-spin relaxation time. That's basically the relaxation time corresponding to the transversal part, and the spin-spin relaxation time is the one corresponding to the longitudinal part. And then we also have a velocity and a diffusion. So note that in these quantities, some of them depend on space and time. So the magnetization, of course, depends on space and time. Also, the velocity, of course, might depend on space and time, whereas all these other quantities only depend on space. And in fact, it's these quantities, especially these three ones, equilibrium, magnetization, and relaxation times, that are used for imaging. So what does it mean? So we have a function of space. So it's basically really a scalar function of space. Each of them is a scalar function of space. If we make an intensity plot of this scalar function of space, it gives us an image. And that's really what is giving us the quantitative image, as one calls it. So it's always an image of a physical coefficient. Actually, at a later stage, we will also look at the diffusion. So the diffusion is, well, I've put a vector, that's not correct, sorry. Diffusion is a tensor, so it's a matrix, in fact. There's some isotropy, so that it's a matrix, in fact, not a higher stage tensor. But still, each entry of this matrix gives additional information. But of course, the more unknowns we have, the more complicated the problem will be. So for the moment, we stay with these three coefficients that we will want to reconstruct. A bit more about what's contained in this equilibrium magnetization. You see, it contains this B0 field. That's this large magnetic field in longitudinal direction, this 1 up to 3 Tesla field. There's some further physical constants hidden here, not going into detail about this. And here's actually the important quantity, the spin density. That's what one actually wants to image. That's a function of space, because of course density can be larger in some places and lower in other places. And this gives us important diagnostic information. So since what we consider is not the spin density alone, but in this combined version of forming the equilibrium magnetization, we use it. Okay, also this longitudinal and transversal part of the B field play separate roles. First of all, for the longitudinal part, it contains this large static magnetic field, this B0 part, plus some perturbation, which sometimes is not that small, so one does not know it, but one sometimes needs to recover it alongside with the imaging parameters. And there's another part, the field gradient, multiplied with a function of space, which is used in order to do the spatial encoding. So if one does the imaging, then this part here will, at some point, you will see it, describe a curve in space that allows us to really do the sampling. But you will see this later on. Okay, now about the transversal component. The transversal component is where we excite, where we impose the excitation. And the excitation is done by a time-dependent function, the radio frequency field, and some also, so to say, hardware-dependent part, which is also sometimes not known and needs to be reconstructed or calibrated separately, which is gives a multiplicative space-dependent factor here. Okay, so that's basically the physical ingredients. Some more notation, some more simplifications. First of all, also in quite useful piece, I should say that I started learning about all these things not much more than, say, 1.5 years ago, especially in that much detail. And it was really fun learning about this. So my purpose today is also to share a bit this fun of learning about these mostly physical things as a mathematician after all. Okay, and something quite neat I found that apparently physicists and engineers do quite often in that context is that one can just represent the transversal plane as a complex plane. So instead of just looking at x, y, we say it's like the Gaussian complex plane, right? And then it's also just one variable. So it's really then just, we have one variable for the longitudinal part, which points always in z direction. And then we have one component, just a single one, but it's complex valued for the transversal part. The reason is for this being so nice is that in the transversal part, we always have this rotation here, which can be nicely described by an exponential function. You will see this in a moment. Very simple. So like describing sines and cosines by e to the I something, and that's something which is very useful here. Of course, since we have convection here, at some point we will see the material derivative appearing. That's just to abbreviate this combined derivative here. Then also usually what we consider, you saw the relaxation times as reciprocals, so it's more convenient to just take the reciprocals and consider them as they are also called relaxation rates. So these R1 and R2. Another important quantity is this so-called Larmor frequency. So one of the coefficients, the gyromagnetic ratio, as it's called, is gamma here, multiplied with this large B field. This gives us the Larmor frequency, omega 0, and because of the fact that B0 is large, also this omega 0 is large. So there will be a high frequency involved in the whole thing, namely in this precession movement. So another useful thing in the context of this complex notation for the transversal part will be to combine the transversal relaxation rate, this R2, and this field homogeneity into one complex valued coefficient. This also makes writing a bit more transparent and short. And this way we can write the Bloch-Torre equation, which in the previous slide, just to one of the previous slides, it was quite a huge object to write it in a somewhat more compressed way, and also somehow more split into transversal and longitudinal part. It's not completely split. So you see there's some coupling here. I will highlight this a bit more. Let's move on with reformulating. So with looking at this Bloch-Torre equation and reformulating it a bit. And what I would like to highlight here is this large high oscillation part. Yes, it's oscillation because, well, if you remove everything else, just keep the time derivative. Let's say it's just a single time derivative. Skip all other terms, and then we have I omega 0. So thinking about what the exact solution of this will be, it will be e to the I omega 0 t, right? So, and this will in fact be sine of omega 0 t and cosine of omega 0 t. And that's actually this fast rotation movement. for really solving the PDEs, for example, numerically, that's a serious obstacle. So you don't want to have something very fast moving, because then you have to use really tiny time steps for resolving that. But it's really easy to get rid of this. We just have to introduce an auxiliary quantity. Of course, you know this, as mathematicians, we know that, how to do this, but it also has a physical meaning. The physical meaning of this is you, instead of just watching the thing rotating, so to say, we have a carousel that rotates very, very quickly. We just jump on the carousel and move along in the rotating frame. Okay, so this changed magnetization, so this so to say, rotating along magnetization, that's just considering the magnetization in a rotating frame, and we know with which speed it rotates and in which direction it speeds. It's a very simple rotation, okay, which helps to simplify this. So now we are in the rotating frame, and now it's really, that's the equation that we are considering. I've highlighted for you to distinguish between, again, the transversal part, which is a single but complex valued function, this m perpendicular, and the longitudinal part, which is mz. And you see here that both of them are coupled. So it's not completely separate. That's a coupling. And in fact, the coupling is due to this P function. Recall, P is the excitation that we do. That's the so-called radio frequency pulse. And in fact, this is something which can be really used as a control. That's actually the control function that, after all, we want to optimize. Not in this talk yet, but later on in our project. Also here, maybe you see from the relaxation terms here, except for this term here, basically the transversal magnetization tries to return to zero due to this term, whereas the longitudinal one wants to return to equilibrium magnetization. Okay, now it's about what we measure. So this was first of all about the model, how the magnetization involves. Now, what can we really measure? We cannot measure the magnetization directly. So what is done is one measures induced voltages, or actually voltage differences that are induced due to a changing magnetic field. So it's really Faraday's law of induction that you might recall from school. So you have a temporarily changing magnetic field that induces an electric current. And in fact, what it induces is a potential difference. If you now go for Maxwell's equations, which is the way, I did not have much physics at school, but what I really learned later on in my life was Maxwell's equations, and one can actually explain this by one of them, namely the one that connects the electric field E. So curl of E is equal to the minus the time derivative of the B field. So integrating the B field over a coil gives us the magnetic flux. And we had a time derivative, so it's the time derivative of the magnetic flux. On the other hand, integrating the curl of E of the electric field. So integrating a curl by Stokes' theorem gives us a curve integral along the coil loop. And so this gives us the voltage difference at the, so to say, at the ends of this loop. Okay, and that has a name. It's called electromotive force, but in fact, it's just a voltage difference. And then on the other hand, one can write the magnetic flux like this. One can write it in terms of the magnetization, which is denoted by B as well, but it's not really a magnetic field. It's rather a magnetic induction per unit current. So it's normalized to unit current. And it's something like a coil sensitivity. So it's typical of the coil that is sensing here. Okay, so there's all kinds of tricks that also allow not only just to measure in sort of combined quantity of the transversal field, but they are both components, X and Y component, but only an average version. So it's really, the important piece here is really we do an integration of over all of R3. So we integrate out space. There's this combined quantity which is called the coil sensitivity. This is really the transversal magnetic field that one gets out of the Bloch-Torre equation as a solution to this PDE. And the outcome of this is really just a time signal. So we get, first of all, we don't get any kind of spatial resolution. Well, we get some by some steering that we do, and we will see this later on. We also get some additional information by not just using one single coil, but an ensemble of N coils that take measurements in parallel. So that's the so-called parallel acquisition in MRI. And so this gives us more information. Okay, so this is what our observations look like. So that's also untypical for tomographic, well, mathematically tomographic problems, because if you think of, for example, maybe you have heard about ultrasound imaging. So in particular, ultrasound tomography, there it's really measuring on the boundary. Or what is maybe even more familiar in inverse problems is electrical impedance tomography, or it's also called the Calderon problem. So where one really does measurements on the boundary of an object and one wants to look inside. Here it's different. One does average measurements. It's also outside the object, but it's sort of averaging, not pointwise. Okay, so here we are back with the full model, including now our rotated and imaginary notation Bloch-Torre equation model. So that's the PDE. And that's the observations that we have. Of course, we also have boundary conditions, usually, but just uses homogeneous Dirichlet boundary conditions, which makes sense because the magnetic field lines will not go very far outside the imaged object, or at least very far outside the whole experimental setup. And they should not, this would not be so good because they are very strong. And we also have initial conditions. Initial conditions, if you recall, we had the beginning, we had this equilibrium position. So the initial condition is just 0 for the transversal part. And it's just the equilibrium magnetization in the longitudinal direction. Okay, and here's our observations that we have. So what we want to have from this time series of observations, we want to reconstruct space-dependent coefficients, and actually even 3 of them, and there's these 3 highlighted coefficients. So let me mention at this point that at some later point in our project, in our MR Dynamo project that we have, we also want to do optimal control of the reconstruction. And so what can be controlled here? First of all, it's this radio frequency pulses here. And then it's also this gradient field. So let me illustrate a bit what the meaning of these quantities is. And this is also illustrating a bit on how these things are usually plotted and explained in this MRI community. So it's really, I have been told that it's really like reading sheet music. So we have these lines, yes, and then we have the notes on them. But yes, each line has a different meaning. So the first line is the radio frequency pulse. So here you see, for example, you have a certain rectangular pulse. That's what we will also see here. And then we have this G field, that the gradient field is responsible for the spatial resolution. And there's further lines that I will not go into detail about. So there's also the recording of the signal and so on and so forth. So we will also in the following consider rectangular pulses. So just a characteristic function of a short interval starting at T0 and ending at T0 plus some epsilon. So our RF pulse will be of this form with a certain amplitude. And in fact, the amplitude, together with the width of the pulse, determines the rotation angle. You see some alphas up here. And in fact, if we, for example, if we take alpha equal to 90 degrees, this corresponded into some certain relation between the amplitude and the pulse length here. How much it takes to really rotate the magnetization from longitudinal to transversal. And one could also do 90 or 180 degree pulses or some angles in between. Okay, so time is running, and I'm sorry, I have wasted the first 15 minutes. Sorry for that again. Maybe very quickly about the forward problem. So this is our Bloch-Torre equation again. And if you look more closely, so here it's mentioned about what kind of boundary conditions. One could also go for other boundary conditions. That's not so important for the analysis because it goes similarly. We look at, first of all, at this problem here, possibly with some non-zero right-hand side, and looking at it more closely and looking where the derivative, the spatial derivative sits. So we have diffusion terms here. We have some advection terms here. Otherwise, there's no space derivative. So it's basically an advection diffusion equation, a system of vector-valued advection diffusion equations. Under certain assumptions, and what I also don't want you to read all the details, basically it's enough to have everything in LP spaces. That's good because our imaging quantities might be not very smooth. They might be piecewise constant or just piecewise smooth. So thinking about, for example, interfaces between bones and soft tissue, or interfaces between organs, quite often this is not a smooth transition, and then it will be just an L infinity coefficient, and that's enough actually for our purposes. The only thing that needs to have a little bit of spatial smoothness, that's the velocity. Okay, but that's okay. So, and with this, one can state an existence results. Of course, it's standard parabolic theory. The only somewhat particular thing about it is that with this result, I wanted also to take into account the possibility of degenerate diffusion, because we will also actually sort of be somewhere in the region between some really strictly positive diffusion everywhere and no diffusion being taken into account, so with an ODE model, or maybe something in between, where in some region one has diffusion and in other regions there's no diffusion. And that's what is basically behind this. Okay, but I think, yes, what the topologies that we use on the imaging and modeling quantities, these are basically these LP topologies without going into detail. So what are the modeling and imaging quantities? The imaging quantities, as was already mentioned, that's the equilibrium magnetization and these relaxation rates. The model quantities is all the rest. So diffusion, the velocity, also these hardware quantities, and also these two last parts are the controls. At some point in the project, we will move them into a separate, actually we are doing this already, moving them into a separate category of control quantities, depending on time, by the way. And we will actually also want to move some of this, in particular the diffusion, towards the imaging piece, because it can also be used for imaging. But we are not yet there. So we have smooth dependence of this parameter to state map here with respect to both imaging and model quantities. That's another proposition. But without going into detail, let's move on to the inverse problem. It's anyway, how much time do I have left? Because the next talk will start at 5, isn't it? Or should I stop earlier?
Yes. If you prefer, we have 15 minutes more. Is okay for you? Finish?
Yes, for me it would be completely fine, but I don't want to interfere with the next speaker. So
Okay, so 10 minutes.
Then I stay
to
with 10
finish at
minutes.
time.
Yes.
Okay, thank you.
Yes. Maybe I also stay very short on the rest. I have spent a lot of time for my own technicalities and for this explaining the model, but I think that's also something. There was very little mathematics so far, but yes, it's maybe that this was also something interesting for some of you. I hope at least. But still, a few words about uniqueness and what I definitely want to show you. So this is our task, reconstructing these three coefficients from these observations. What we want to show is that, yes, these observations are sufficient to reconstruct these three coefficients. You will probably or hopefully say that's nonsense, formulated this way, and that's true. We cannot hope for reconstructing a especially three-dimensional, actually, and even especially three-dimensional functions or three variate functions from just a function of time. That's not possible, even if this function has several components. So this n is not really large. So we cannot assume that this capital N is a very large number. So we cannot, so to say, send n to infinity to do the trick. The trick is, in fact, to fill the space by a certain curve evolving over time. And that's driven by this G here. Still, we can never fill the whole space with a curve of finite length. And so it will always be that these quantities can only be uniquely determined on a certain subspace. That's an important piece. So for showing uniqueness from this setting, we first of all get one step back and remove diffusion and convection. This way we end up with a set of ODEs, and it's infinitely many ODEs because it's an ODE at each and every point in space. So all these quantities still depend on space. So at each spatial point, we have an ODE in time, or actually a system of ODEs in time. That's the so-called Bloch ODE. So first of all, there was the Bloch ODE, and then Torrey came and introduced diffusion. So we travel back in time to Bloch and look at this ODE. Well, it's a linear system of ODEs. It's trivial to solve it. Well, not completely trivial. One has to spend a bit of time with pencil and paper and write down things, but then one can come up with explicit solution formulas. Well, there's still some time-dependent parts. So there will be still some, from the variation of constants formula, you will have some contribution from that. But if you assume that P is of special form, so this rectangular pulse, you have a very special function of time, and then you can again go ahead and resolve with respect to time. Okay, and solutions after some computation, they look like this. Okay, one can really, for example, if one does a rectangular pulse, which turns the magnetization by 90 degrees, for example, the solution looks like this. Very nice, quite short, explicit formula in terms of the equilibrium magnetization. And okay, it contains this K of T. K of T is the integral over time of the gradient field. Okay, that's the time integrated gradient field. And it's a vectorial quantity. Okay, so it's defined in such a way that we have this vector 2 pi. The reason for this is if it has this vector 2 pi, then at least for physicists, it reminds of the Fourier transform. As mathematicians, we might not need the 2 pi, but that's what they usually do. Okay, there we go. And then just plugging in this formula into our observations. So this was just the coil sensitivity integrated against this magnetization vector. Now we plug in the formula. While we move part of it to the other side, we say, well, this R2, let's for the moment assume that it's close to constant, and we can move this e to the minus R2 times t over to the measurement, also minus I. so that it looks more clean on the right-hand side. Okay, here we go. That's our formula. And moving further, we see, well, it's really a Fourier transform. So because we integrate over R3, right, then we have this argument. That's what we usually do. Usually we say it's, say, omega or psi or something times R. So it's some vector because we are in 3 space dimensions times R. We integrate with respect to R. So what we do is we Fourier transform this product here of C and M. So it's really the Fourier transform of C times M evaluated at K of T, yes, because that's this K of T up here. Okay, this explains MRI viewed as Fourier inversion from sampling along a curve. That's what it is. And this way one can get there's all kinds of clever ways of doing the inversion such that one gets the maximum out, and in particular such that one gets the maximum out. So of course it's designing this G of T such that this K curve, so that's the so-called K-space trajectory here, such that it collects as much information in Fourier transform space, so in K-space, and then we Fourier transform this back to physical space. In fact, one can do this. So that's what I said. So the observed data is basically a spatial Fourier transform of the equilibrium magnetization. One can do similar tricks with the relaxation times. So all other kinds of pulse combinations, and obtain explicit reconstruction formulas. However, in order to end up with these formulas, we have, in fact, we do a sort of limit as the pulse length tends to 0. So not just by chance, it's called epsilon. So it's a limit as epsilon tends to 0, which is not really completely physical. And also we have swept the spatial variations of this R2, for example, under the rug and all kinds of other things. So, and it also works just in the very specific setting. So recall that the formulas that I've shown you, or at least one of them, were derived for very particular rectangular pulses, not even for arbitrarily spaced, but very, very particular ones. And on top of this, we have completely neglected diffusion and convection. And so in order to return to the more physically relevant model, we return from Bloch to Bloch-Torrey. But we don't turn completely away from Bloch. Of course, we keep in mind that, yes, with the Bloch ODE, at least with very special excitations, we can do explicit reconstruction, meaning that we do have uniqueness for in some simplified settings of Bloch ODE. And now, this is really now the end of my talk. Not going into detail about this. Just by closeness, so to say, of the Bloch PDE, Bloch-Torrey PDE to the Bloch ODE, and also reverting these simplifications, we can show uniqueness in the full Bloch-Torrey PDE. And that's mathematically non-trivial. The reason for that is going from a pointwise ODE in space to something containing diffusion is now understood from the mathematical side. Going from an ODE pointwise in space to a diffusion PDE, this makes a big difference. Because the diffusion PDE, that's something which gives a lot of smoothing. It gives infinite speed of propagation of perturbations. And after all, it gives also additional spatial regularity, which the ODE does not give. For the inverse problem, that's also very, very important. And so, yes, it's an interesting piece of mathematics. Unfortunately, I was not able to tell you much about this, but maybe it's a bit of a teaser to look a bit into the things that we have meanwhile published on this. And just a very final word on this, with this infinite speed of propagation that diffusion gives. This is also another way of showing uniqueness, because diffusion also can help to transport information, and that this would have been the second part of the uniqueness proof, the diffusion-based one. But let me now finally stop, and thanks a lot for the attention. Apologize again for the delay. And if you still have questions, and if time from your end still permits, I'm happy to take them. Otherwise, please just feel free to drop me an email. That's also okay, of course. Or look at our homepage or look into our papers.
Thank you. Thank you, Professor. Good to know. Thank you for this interesting talk. Okay, remember, if you have a question, you can write on YouTube chat. Let me check quickly if you have some question. I think we don't have, but maybe I'd like to ask you. Okay, let me check again. Okay, yes, we don't have. Can I ask you something about? I am not sure if you mentioned about these points, but because you use perturbation estimates to move from the simplified block ODE setting to the full block Tori equation, right?
Yes, exactly.
So my curiosity is more a curiosity. How sensitive are these estimates to the magnitude of the diffusion term?
Yes, that's in fact that's a nice question. So that's actually this decisive quantity. So of course, since it's a perturbation, well, in fact, I did not tell you the whole truth. So what I did here in order to prove uniqueness for the Bloch-Torre PDE was not really starting completely from Bloch ODE, but looking at the frequency, so k-space formulation of the Bloch-Torre PDE with constant coefficients. Because there's also a possibility, which I did not have time to mention here, to write everything in k-space. So to say, do a Fourier transform with respect to the space variables, and then end up with a PDE in k-space, still with time dependence, so with a time derivative. And if one moves into, maybe I can demonstrate this here a little bit by means of the equation, just very quickly. So here we go, for example. So no, it's not the right one. Sorry for that. This one. So if we do a Fourier transform, then of course the gradients will be, so to say, replaced by their symbols. It's because it's really spatial. One can actually go ahead and do something like pseudo-differential operators also here. That's, by the way, used for doing non-local diffusion, which also plays a role. So, but there's no, so this, of course, these space derivatives after Fourier transform, they are just multiplication operators with the k, so to say. But we have an R here, and the R here becomes a gradient. So if you have a very good imagination, maybe you can imagine that out of all these terms, what is left over is still the time derivative, of course, and there's a gradient term here. And so what pops out of this is a transport equation. So time derivative and a gradient with respect to the k variables. And again, one can go ahead and solve this transport equation, at least for constant coefficients, because otherwise it's full of convolutions, which makes life very complicated. And then one can go ahead and starting from that do the reconstruction. But still, in order for one still, this only works for very specific pulses, and then to generalize pulses, one needs to do, so to say, to step away from this simplified setting and do the and do the perturbation argument. And in fact, it's about not so much about how large the diffusion is, but how much it deviates from a constant. at least for the mathematical piece of it. For solving the inverse problem, then really computationally, diffusion plays a big role, because if there's a lot of diffusion between the object that we want to image and the observations that we want to take, it's clear that information will get lost. And this loss of information, the more information is lost on the way, the more is smoothed out. If you think of the heat equation, for example, it's very much smoothing. It's smearing out all details that you might have at the beginning. You cannot see them after a while. And so this makes inverting the problem very tough. So the larger the diffusion is, really for stability of the inverse problem, or for reconstructibility numerically, that's really a crucial thing. So magnitude of the diffusion, as you already conjectured correctly, is an important issue here.
Okay, I see. Thank you. Okay, now I can see we have another question on chat. The question is, for certain large T, can we expect less influence in the diffusion term for the block-Toric equation? And maybe work in a simplified form of the equation for certain T large?
Okay, large T, yes. The question, what will happen for large T? The question, well, it will probably converge if you just let T tend to infinity. So I did not think about this, as you can notice, but let's think about it a bit together. So removing these terms here, because they will be switched off after large time, what will happen is, well, it will converge maybe to some equilibrium. Maybe it will just simply converge to the equilibrium magnetization. That's what it should do. But if it keeps being excited by this control term here, of course, something else might happen. One might think about, for example, if one chooses this g of t as a time periodic function, for example, that maybe the system goes into some sort of limit cycle, that if one goes through that sufficiently often, helps us to end up with something, a simpler structure from which we can extract information more explicitly. So sorry, I'm only brainstorming now, not really answering. But thanks a lot for the question.
Okay, thank you. Okay, it looks like we don't have more questions. So thank you again, Professor Barbara.
Thanks a lot for coming. And thanks a lot for the invitation.
Thank you. Okay.
Okay,
so
we'll stop sharing again.
Okay. Our next, we are ready, I think, for our next speaker, our next talk. We have with us Ruth Alejandra Torres. Are you here? Ruth, I can see you, but I cannot hear you. Ah, okay. Yeah, okay. Let me check.
Hi.
Okay,
Hi,
now
Karina.
you can.
Yes. Thank you, Karina. Good morning and good afternoon, everyone. Thank you for joining us. Let's move on to our next talk. Maria Angeles, are you here? Yes?
Yes, now I can speak. Hello,
Hi.
everyone.
How are you today?
I'm fine. Let me share my slides. Can you see them now?
Yes, I can.
Perfect.
Very much. So, if you like, let me introduce you, please. Okay, my name is Ruda Alejandra Torres, and it's my pleasure to moderate this lecture. I'm very happy to introduce our next speaker, Dr. María Ángeles García Ferrero. María Ángeles García Ferrero is a researcher at the Instituto de Ciencias Matemáticas in Madrid. She previously held research positions at the University of Barcelona, the Basque Center for Applied Mathematics, Heidelberg University, and the Max Planck Institute for Mathematics in the Science in Leipzig. Her research interests include local and non-local partial differential equations, inverse problems, geometric analysis, fluid mechanics, and mathematical physics. In 2019, she received the José Luis Rubio de Francia Prize, awarded to the best young mathematician in Spain. We are very happy to have her with us today. María Ángeles, thank you very much for joining us. Your talk will last about 45 to 50 minutes, and after that we'll have some time for questions. So whenever you're ready, the floor is yours. Thank you.
Thank you very much, Ruth, for so nice words. And I want to thank all the organizers. I'm truly honored to participate in this Congress. So thank you very much for having me here. So I'm going to talk about another inverse problem. So somehow I'm going to continue the general topic by Professor Barbara Kaltenbacher. Although I was, preparing some more general introduction to the topic of inverse problem and then moving to the particular inverse problem I'm talking about. So here I was collecting some pictures of different inverse problems. So what is an inverse problem, roughly speaking? So it's a kind of problem where we have some phenomena, and we are able to measure some results that this phenomenon produces, and then we want to know better the phenomenon itself just by these somehow indirect measurements. So in the first line, you can see three different situations, but very, very closely related, in which what we have is, so let's focus, for instance, in the case of the dolphin. So the dolphin, the animal produces some sounds, which at some point hit some obstacle, in this case, for instance, a fish, and these waves, the sound waves, hit the obstacle, and then an echo is produced, so the waves are scattered, and then the dolphin receives this echo, and the dolphin is able to determine how far or how big the fish is, depending on this echo. So more or less the same ideas hold behind the sonar or the ultrasonography. In the second line, I was referring to some techniques used in medical diagnosis. So in the second case, we have exactly the technique that Barbara was explaining just before this talk. And in these cases, so thanks to some physical phenomenon, we are able to see what's happening inside our bodies, for instance, just by taking measurements from the exterior. So in all these three cases, we are not opening the body to see what's going on inside, but just taking measurements on how the tissues behave to some physical phenomenon like radiation or what Barbara was explaining earlier. And in the third line, well, I was collecting like different things, and one related with imaging, and the others related with other physical or techniques in physics. So let's move to the particular inverse problem for the conductivity, which is the problem of determining the electrical conductivity of a medium by taking measurements on voltage and current on the boundary. So the problem is usually named after Calderon. So here we have Alberto Calderon, who was born in Argentina. Before becoming one of the most famous analysts and mathematicians in the last century, he was working for a company, Argentinian company, for oil prospection. So he was thinking about the following problem. So he was given the problem of determine whether there's oil behind some part of the earth or not, without making a hole. So the idea he was thinking of was to place some electrodes of the earth, put some currents, measure some voltages, and since the relation between the voltage and the current on the boundary could be or would depend on the conductivity inside the earth, which in turn depends on the kind of material we have. So it will be different if we have oil or like concrete material for behind the earth. So he was trying to see if indeed that there was oil or not. So when we talk about this kind of problem related with what's behind the earth or something in geophysics, we will talk about the electrical resistivity tomography, although the problem in mathematical terms is usually known as the Calderon problem. The same idea lies behind the electrical impedance tomography, which somehow is more related or more applied in the medical context, which again deals with the fact of determining the conductivity now inside a body, in this case of a baby. And the idea is, okay, let's put some electrodes around. Let's take measurements on voltage and current on the surface of the chest, in this case of the newborn, and then let's try to determine the conductivity inside. And in this way, so we can, for instance, to monitor how the lungs of the baby are working, or in other cases, we could also see if there's a tumor or some related problem. So let's move on in the mathematical context. And in order to formulate the problem, let me start with introducing the conductivity equation and the quantities we are going to deal with. So we are going to deal with a medium, with an object, which will be represented by a bounded smooth domain denoted by the letter omega. And inside this medium, we have a function which represents the conductivity, the electrical conductivity, how favorable the material is or the object is at any point to the current, to the electrical current. So this will be a function, a positive function, bounded from below and above by positive constants. And then we have two other physical quantities, the voltage and the current density, which is a vector. And they are related by the formula you can see here, which is, roughly speaking, the Ohm's law. So now let us consider for a moment that our object, and this will be the case, I mean, it's not only for a moment, that our object is somehow isolated. So we are not going to allow that electrical charges appear or disappear at any point. Then, if this is the case, the flux, so the total electrical charges that leave or enter in any particular small volume inside omega are given by the flux, which is this quantity here. But since there are no points where the electrical charges can appear or disappear, this quantity must be equal to 0. And this must be true not for this particular domain I was representing, but for anyone I can plot inside omega. So now let's apply the divergence theorem, changing our integral on the boundary of this volume by the gradient of the vector we had earlier, which is this thing here. And now this is, again, this integral is 0 for any possible volume or domain inside omega. And therefore, what is inside must be equal to 0. But just recalling how the current density is related with the voltage via the conductivity, this is what we have at the end. So this is our conductivity equation. So now we have the ingredients to formulate the forward problem related to the inverse problem. So for the forward problem, we will start with the electrical conductivity of a medium that now we know it's a function omega, or gamma on the domain omega. And then what we are going to measure are the disperse of voltage and current density through the boundary. So we have the pair of B and then the normal component of the current density, again on the boundary of our domain, which by the previous relation we saw before is given by the normal derivative of our voltage times the conductivity on the boundary. And how all these things are related? I mean, not only, this voltage here with this quantity here, right? So they are related by the conductivity problem, which is nothing else but the conductivity equation we just derived together with a boundary space there exists. Can you still hear me? I'm seeing this is unstable, the connection.
Yes, we can hear you.
Okay. In case of any problem, well, I will try to check. Thank you. So yeah, as I was saying, for any function g in the right space, there is one and only one solution of this problem here, and this solution must be understood in the right sense, which is written in this box here, but I'm not going to give all the details. This is related, so this condition here to be bounded from below and above by positive constants, which is a reasonable assumption coming from physics. And now, let me introduce so an operator which somehow encodes the information we are going to measure, or in this case, what we get in the forward problem. So this operator is the so-called Dirichlet-Neumann map, which roughly speaking, for any possible voltage or function on the boundary G, we solve this problem. We have seen that this problem has a unique solution. So then we take this solution and we consider its normal derivative on the boundary multiplied by the So now our question is whether we can determine the conductivity gamma from the knowledge of this Dirichlet-Neumann map that again encodes the pairs of current density through the boundary and voltage on the boundary. So the main questions for this problem, but in general for any inverse problem, Barbara was also talking about this, are these three ones. So uniqueness, meaning that if we have two Dirichlet-Neumann maps which are the same, can we say that then the conductivities are the same? If we go back to the applications, for instance, in the case of medical imaging, so in order to have a really meaningful diagnosis technique, we should have something that, depending exactly on what we measure, it determines what it's happening inside the body, right? Because otherwise, I mean, maybe we are measuring the same things in two very different cases, and then, I mean, the information is completely useless. The second question would be stability, which is, okay, now we don't know that the two Dirichlet-Tunnelman maps are the same, but they are very close in some sense. So then what we should expect is that the conductivity should be close, right? Because again, going back to the applications, whenever we take measurements, we are going to have some errors. So even if the error is small, maybe, I mean, if this question we have here, so if the answer is no, maybe we are measuring something close to the reality, but we are determining something very far from the reality. And maybe, I mean, in terms of medical diagnosis, this is completely far from the real situation, and therefore, again, the technique is useless. And finally, okay, this is very good, but then, I mean, I want to get something that that really allows us to see what's going on behind the body or behind what we want to determine. So we could need a reconstruction algorithm such that, given this Dirichlet-Tunnelman map, we can get the conductivity this operator is related with. So here I'm mentioning some main answers to these main questions. And you can see that there's a difference depending on the dimension. So in the case of one dimension, in this case, it's like having a wire that we cannot solve the Calderon problem. In the case of two dimensions, for instance, the answer to uniqueness was given in full generality, meaning that the conductivities are bounded, as we were seeing before, by Astal and Paivarinta. And in the case of 3 or higher dimensions, well, there are a lot of contributions, but here I was somehow referring to two situations. The first one is to conductivities which are smooth enough, which means C2 up to the boundary. And then in this case, the answers are given by, for instance, Ullmann, Silvestre, Alessandrini, Nachman, and Novikov during the 80s. And then for less regular conductivities, we can start seeing different papers, like reducing the regularity conditions up to Lipschitz conductivities, which is the case which is believed to be the optimal case inside the class of Helder regularity conditions. And here, I mean, the range of years where these results were produced, you can see it's much bigger. And before going forward, let me just highlighting one of the experts in the Calderon problem, who started proving the uniqueness together with Sylvester, but he continues to give a lot of answer to these unrelated problems, and he is Gunther Ullmann, who works now at Washington University, but he is from Chile, so that's why I wanted to emphasize his name. So from now on, I will focus on the case of 3 or higher dimensions, and we will see his result together with Sylvester for uniqueness, or at least the main ideas and how these ideas can be used in the other main questions. Okay, so here we are going to consider that our conductivity is C2 up to the boundary. And one of the key points is the reduction, or is to see that our conductivity equation or our conductivity problem can be rewritten or equivalently written in terms of a stationary Schrödinger equation. So if you change or if you perform the changes you can see here, our previous boundary value problem for the conductivity can be written as this problem, which in this case deals with the Laplacian. and then a potential Q, okay? So here you can see that the Q is equal to the Laplacian of the square root of the conductivity over this square root. And that's, I mean, ensuring that our conductivity is C2 tells us that this quantity here is L infinity. Of course, I'm also taking into account that the conductivity is bounded, I mean, from below by a positive constant, okay? In the same way, we had a Dirichlet to Neumann map here. We have another one related to this problem, which let me say now before I forget. So in the case the Q we are seeing here is related with gamma like that, this problem is again well posed, meaning that for any f in the right space, there is a solution in the right sense of this problem, and the solution belongs to the right space. Okay, so we could consider this problem like in general, not necessarily with a potential Q coming from a conductivity, but in this case, I mean, the problem could be not well posed, but let us assume if we are thinking of this problem like in general, it is always well posed in this sense, or if not, let us think this problem is always related with a conductivity problem, and then for sure it will be well posed. And then again, this Dirichlet to Neumann map makes sense because for any f, there exists a unique u, and we consider the normal derivative of this solution on the boundary. So remember, we were interested in solving the inverse problem, giving us the conductivity from the knowledge of the Dirichlet to Neumann map associated with this conductivity. So what we can try to do is to use the inverse problem to this new Schrödinger problem, and yes, I mean following this path, right? So I will focus on this part, so on the inverse problem for the Schrödinger equation. But in order to go from here to there or back from the potential Q to gamma, there's something else we need to know, and we need to know it only from our original measurements, which is this Dirichlet to Neumann map. So what we need to know is the conductivity and the normal derivative of it on the boundary. Okay. So for instance, if we if we want to recover gamma from Q, so we know that gamma is related with Q like that. So somehow we can solve the PDE related with gamma. So we know Q, but we need to have not only an equation, but a problem. So that's why we need to know something on the boundary, okay? And this is what the paper by Conan Vogelius tells us how that we can recover gamma and the derivatives from the knowledge of the Dirichlet to Neumann map. So now, as I said, let's focus on this inverse, or on this step, on this inverse problem, and let me show you the main tools. So one of the main tools is this relation between what we measure and what we want to determine. So this is usually called the Alessandrinis identity, and it can be easily derived by integration by parts, for instance. So here we have this relationship, but we have the functions u here, which are the solutions of the Schrödinger problem for the corresponding Q with Dirichlet data corresponding to the Fj. Okay, so this is how all the quantities are related. And the second main tool, which was obtained by Sylvester and Ullmann in the 80s, is the existence of very special solutions of this equation for any potential Q. So only the equation, I'm not imposing any particular boundary data. So these solutions look like what you can see here. So firstly, we have an exponential with theta being a complex vector such that multiplied by itself is equal to 0. So now let us consider this exponential only for one moment, and let us consider or let us apply the Laplacian to this exponential. So the Laplacian or the second derivative, and let's consider x is of one variable. So the taking the Laplacian is like moving this vector theta like outside, right? So we will get theta times theta and then the exponential, which always appears. But if theta times theta is equal to 0, then the Laplacian applied to this function, to this exponential, gives us exactly 0. So this function here is a harmonic function. Of course, we are looking for solutions of the whole equation with the q. So this part solves the equation without q, right? So in order to have a solution of the whole equation, another term should appear. The good thing about this extra term is that they prove that this extra term disappears or goes to 0 in some sense when our vector theta goes to infinity in modulus. Okay, so this is this is roughly speaking the properties of the how the CGO solutions, so CGO comes from complex geometric optic solutions, look like and what. So this is a very key or a very brief point about how this can be, so how this U can be constructed. So notice that this is chosen and at the end is solving a problem for R. So this is how R can be computed. So R, you can see here, is something depending on theta. So theta is hidden in this operator here, which is the Laplacian conjugated with the exponential. And then, okay, we have to invert this operator and then to invert this one, which can be done because what they saw was that this operator here, so its norm decreases with theta, with the modulus of theta. So then we can make this small enough such that multiplied by q is smaller than 1. And then using the Neumann series, this can be inverted. But let's not enter too much into details. Let us see how these main tools, the Alessandrini's identity and these special solutions, the CGO solutions, can be used in order to prove the uniqueness of the Calderon problem. So uniqueness, remember, means that two Dirichlet Neumann maps, now for the potentials Q1 and Q2, are the same. So by the Alessandrini's identity, we get 0 in one of the sides, and therefore this is what we obtain. So Q1 minus Q2 multiplied by the product of two solutions, one corresponding to Q1, one corresponding to Q2, this is equal to 0. And since now we are not seeing the boundary, because whatever happens at the boundary, it's going to be the same. It's going to be 0, right? I mean, so this is the same, so then we don't see anything else. Then we can use here, in particular, CGO solutions. But let us choose CGO solutions in a smart way. And smart way means that we choose the thetas, the vectors, complex vectors, which appear on the exponential in a good way. So this way is, okay, let us take C, now a real vector, okay, real vector. And then let us construct theta 1 and theta 2, so each one related with one of these solutions, CGO solutions, in such a way that, of course, they must satisfy the condition for getting a CGO solution. And then this extra condition, that their sum is equal to minus yc. And then the extra thing is that we can make the modulus of theta as large as we want. So here you have the particular way of constructing or of expressing these vectors, complex vectors, theta 1 and theta 2. It's very, very important, and that's why we were saying we are working with 3 or higher dimensions, that this can be done if and only if we are in 3 or higher dimensions, because in 2 dimensions, there's no way of fulfilling all these conditions at the same time. We need 3 linearly independent directions in order to construct these vectors. So now we have them. We have the CGO solutions related with them and the corresponding potentials Q. And then, okay, this is what Alessandrini's identity is telling us. And let us substitute the solutions by the expressions we know. So this is what we get. Here you can see that the fact of having theta1 plus theta2 equal to minus yc is reflected in this point. Now remember that the terms are were disappearing in some sense, or is like in L2 sense, when the modulus of theta is large enough. And the point is that we can do this, okay, as I was saying before. So if we take if we take the modulus of theta going to infinity, these contributions are going to disappear. And the only one which survives is this one, which is nothing else but the Fourier transform of the difference of the potentials, or more specifically, of the potentials extended by 0 outside omega, okay? Because here, we and if the Fourier transform is equal to 0, then the function will be 0 itself. And that's how we conclude the uniqueness. Very briefly, some comments about the stability. So in this case, the result is due to Alessandrini, again in the 80s. And well, here I'm writing the stability is conditioned and logarithmic. Let's see what this means. So what we are going to do is exactly the same, but now if we do the same, this is going to grow, okay? Actually, it can be seen, that this quantity here can be bounded, as you can see there, but then so in this case, we need to know how the boundary of the CGO solutions behaves. So because this is not going to be 0, right? And it can be proved that this grows with the modulus of theta. So this quantity here, although maybe this thing is small enough because our exponentially with the modulus of theta, while this
Okay, it seems we have technical
I'm
issues.
back.
Hi, Maria.
I don't know, sorry, I don't know when.
I can't hear you. Something is happening again.
now?
Yes. I can
Okay.
hear you and I can see your presentation.
So I'm not sure when I got disconnected. So I don't know if I was able to say something about these two
Yes.
contributions. Yeah?
Yes.
Okay, perfect. So then, as I was saying, so I need to assume that our potentials are bounded, okay, in the L infinity norm, and this is what is related with having a conditioned stability. So we don't have stability in general, but we need to assume some a priori information to have some kind of stability, okay? And then the second thing about being logarithmic is that when we try to do this balance between these two terms, what we get at the end of the day is something, as you can see here, at least for small errors, or at least for when this quantity here is small enough. So you can see something which depends on a logarithm, which in terms of applications is not very good in terms of for instance, having a reconstruction algorithm in a computer. Nevertheless, this behavior is proved to be optimal. So the only way of getting something which behaves better, in the sense that the propagation of errors between measurements and determinations, the diagnosis we are looking for. So the only way of getting something better is by assuming more things about the conductivities. And in order to finish, I have some extra minutes. So here I wanted to, I was somehow talking about some results for less regular conductivity. So as I said, the best known results are for Lipschitz conductivities. As far as we focus on the Helder regularity conditions, okay? So you can see that there were some intermediate results for, there are more, but here I was just mentioning a few, but in particular for C1 conductivities or Lipschitz conductivities with small constants. And at the end, so the case of Lipschitz conductivities. So in this case, the diagram to prove or to study the inverse problem is slightly different. So now we are not going to deal with the Dirichlet-Neumann map related to the Schrödinger equation because like this line here, so that map didn't have a right sense. And in particular, the Q here is no longer a function. It's going to be, it can be understood as a distribution or as an operator, but no longer a function. And you can see here how it behaves depending on gamma. So again, for this step, we need to know the conductivity at the boundary, which again is possible by this result by Alessandrini. And then let us focus a little bit on this step, and in particular in the reconstruction, which I was not mentioning earlier. So in this case, remember we don't have the Dirichlet-Neumann map for the potential Q, but we can still write kind of Alessandrini's identity relating the Dirichlet-Neumann map for the conductivity with the potential. So, okay, in the previous Alessandrini identity we saw we had a couple of potentials. Here I'm taking a couple of potentials, but one is zero. That's why it's not present here. Okay, so this is the potential equal to zero, which is related with the Laplacian, so the conductivity is equal to a constant, 1, for instance. And here we have U is the solution of the problem with F and Q. U0 is a harmonic function. Okay. So let us try to use the same things we had earlier. So firstly, for the right-hand side, if we use our CGO solutions or CGO solutions which behave like what we were seeing, and we take the limit, we could be able to get the Fourier transform of Q, right? I mean, just doing the same as I was showing you earlier. But what about the left-hand side of the equation? So this is known, the conductivity and the boundary is known. This is the Dirichlet-Neumann map for the harmonic, for the Laplacian. So Dirichlet-Neumann map for the harmonic functions. This is chosen, but what about this? So this is the boundary behavior or the boundary value of our CGO solution U, which we know it exists, how it can be constructed, but how is F, I mean, explicitly, so the independent of Q. So remember F has this form here, which depends on Q. So after manipulating it a little bit, it can be written as this thing, so F minus this exponential, so the theta here is chosen, no problem. So looks like this, okay? And now let us consider this operator here, the inverse of this displaced Laplacian, has a kernel, and we can write the solution as you can see here. So here we have the exponential, another exponential, okay, no problem, Q times U. So now, what happens if this function here, which is this kernel times these exponentials, is harmonic in the variable y? So if this is harmonic, we have a harmonic function, the function u and q. Nothing else but what we have here, okay? With u0 equal to this thing here, which we can expect having something like that if x is not equal to y. So if we need this to be true for y in omega, x should be outside omega. So then if this is harmonic, this would be like some u0, and then we can apply the Alexandrin's identity again. And once we do that, so here, whatever it appears is something known, this is known, and we can write everything as an operator applied to the Dirichlet data we are looking for. So now we have a relation between f and f via this operator, right? And then, okay, so can we get this thing here? So in the results I was mentioning for the C2 conductivities and also for the C1 or Lipschitz with a small norm, the way they were constructing the CGO solutions was in such a way that this was true. So the kernel appearing in order to write the solutions satisfied that this function here was harmonic. And therefore, the reconstruction results were using that. In the case of Lipschitz conductivities, the result for uniqueness by Pedro Caro and Keith Rogers was not using the same kind of techniques. And therefore, the kernel they were getting was not ensuring this property here. So, and this is my contribution to the topic, we had to somehow reconstruct the CGO solutions in such a way that this function here was harmonic again, and then the reconstruction argument could be applied. And at the end, I mean, as I said, we have a relation with f here and there, so yeah, we can write f as you can see here, and this makes sense provided we can invert this operator, which is something to be proven. So just in the last minutes, I mean, I'm not going to give more details on that, and just a few remarks about other questions and other results. So this is not, I mean, it's very, very far to be complete. It's just a few ideas, a few results I wanted to mention. So firstly, about somehow more realistic situations on the Calderon problem. So one is about partial data, meaning that we don't know the Dirichlet-Neumann map on the whole boundary of omega, but only on one part. So there are results which, I mean, somehow they into account the geometry of the part which is not known, or something about the potential near the boundary or something like that. Another situation is about finite measurements. So knowing the Dirichlet-Neumann map is knowing an infinite quantity of information. So what about having only a few pairs of Dirichlet and Neumann data, or voltage and current through the boundary? So there are also results in that respect. So you can see some articles in the slide. Another kind of context I wanted to talk about for the Calderon problem is the anisotropic Calderon problem. So during this talk, gamma was a function, but more realistic situation is that gamma is not a function but a matrix. Okay, and then same questions appear. This is in general an open problem. There are only some partial results on that. And the other problem is another context is the case of the fractional setting. So here I am mentioning like the what is known as the fractional Calderon problem, which is the same as we had earlier for the Schrödinger equation, but changing the Laplacian by the S Laplacian, by the fractional Laplacian, and defining the Dirichlet-Neumann map. Depending on that, which is a map from the now Dirichlet data, which is the function outside omega, because this operator is an operator which takes into account how the function behaves everywhere in order to compute how it is applied to a function in a particular point. And then, well, this corresponds to the Neumann data. So here, the thing I would like to highlight is that uniqueness and even reconstruction under some conditions holds from one single measurement. So before we were saying something about, okay, what happens if we have finite measurements, and in this case we need Q or we need to assume more things about Q, like being in a finite dimensional subspace. But here it's not necessary, only one single measurement. So only for 1F, knowing the Dirichlet-Neumann map, even in some bounded domain in the exterior of omega, is enough to recover the potential Q. And yeah, finally, just to talk another application of this problem is something more recent, which appeared some years ago, which is the potential use of this inverse problem to classify strokes. So there are two kinds of strokes. One is ischemic, one is hemorrhagic. And the conductivities related with these two situations are very different. So in this article, the authors were proposing to use this inverse problem in order to determine which kind of stroke happened in situ, so the measurements to try to recover the patient can be applied very quickly, which is very important in this case. And yeah, if you don't mind, I would like to use my final minute to do a short advertisement, because I guess, somehow I'm here talking about my research because my connection with the European Math Society, the EMS, and I would like to draw or to get your attention, just in case you are interested in some opportunities, mainly funding opportunities the EMS has for mathematicians outside Europe. And this is done through the Committee for Developing Countries, which is devoted to provide support for mathematicians and mathematical activities from the Global South. So in particular, there are two types of funding opportunities. One is for individual travel grants, and the other is to support scientific meetings organized by institutions in the Global South. There are two rounds for application, and the other thing, which is not a funding opportunity, but another activity by this committee is the award of the IRC label, Emerging Regional Center of Excellence label. And the application for this one is really close, I think. But yes, I mean, if you have any question or you want to know more about this, here you can find the information. I just wanted to make you aware in case you weren't, and you may get interested in this about these things. So that's all from my side. Thank you very much for your attention. Muchas gracias and muito obrigada.
Thank you very much, Maria Angeles, for your talk and for this last information. That this is very useful for us. So let's see if we have any questions in the chat. If you are watching on YouTube and have a question or a comment, feel free to post it in this moment in the chat, please. So let me see. Adrian Franco Cruz said, thank you for sharing so interesting talk, dear teacher. We have here a question from Julio César Delgado Valencia. He asks, what is the range for S in fractional Calderon problem?
So thank you for the question. Yeah, so S. Firstly, S was considered to be between 0 and 1, but similar results can be proved to be true for bigger S. So bigger non-integer S.
Thank you. At the moment, we don't have any more questions. So I think that's all. Maria Angeles, again, thank you very much for joining us today, for your talk. And thank you as well to everyone who joined us today. I think we will now take a short break and we'll back in an hour. Yes, can you confirm me, Karina?
Yes, exactly. Okay, yeah, it's okay. It's
okay,
good.
so thank you very much.
Maybe sorry, Ruth. Hi, Ruth, how are you? Sorry that I didn't say greetings to you. Sorry, I just have a question for Maria Angeles, and I don't resist. Maybe I think it's a good opportunity for me to make this question. Maria Angeles, first of all, thank you very much for your talk. I think, considering the topic, it has been wonderful. I have a question about slide 7. If I can make maybe an specific question, because I am thinking, okay, here omega is a domain, right? But I am thinking about the strategy that maybe you are explaining when one is thinking in generalization of the problem to manifolds. Please, I just want your opinion, because it seems that you want to do is to construct many solutions as possible, right? U1 and U2, in such a way that the product is somehow dense
Exactly.
in O2. Okay.
So yeah, it's another way of seeing it. Actually, it depends on the talk. I say one thing or the other. That's exactly what we want in order to prove uniqueness. So it's better seen here. So in order to see that this is 0, I mean, we just need that this product here is dense. So the point is that harmonic functions, so we can, I mean, if we work under the situation of having harmonic functions here, then this is true, right? Because it's exactly what I was doing here. So these functions, I can combine them. So with theta j multiplied by itself being equal to 0, these are harmonic, and then the product can be chosen to be this one, this thing here, and this. So these exponentials are dense in L1 actually. And now somehow we want to do the same, but that's not longer the case. So we don't have density unless we take this limit. But this is exactly what you were saying. We are looking for density, and this is how, I mean, the case of the fractional Calderon problem is solved very quickly, because in the case of the fractional Laplacian, So so the solutions of the fractional Laplacian in some omega are dense in L2 of omega. So then we can approximate any function by S harmonic function, and then okay, here we can put one. I mean any constant or whatever.
Okay.
I mean the
It's
approximation to any constant. So
okay. It's okay with you if I share the few questions more that I have in
yeah,
mind?
sure.
Because okay, the topic is very interesting, of course. I think it was page 11, sorry. Page 11 where you were the but this is
So here there are many details which are hidden.
right,
So
right. Details that are hidden because at some point you mentioned some you were estimate the operator norm of some resolvent for the Laplacian, right? Resolvent for the Laplacian at some point, probably
so sorry, here or
maybe before,
so
because there
before
were some.
maybe you see
Here,
this one?
there, right,
Yeah,
insane.
so this is not exactly the Laplace, I mean, without the minus one, is not the Laplacian,
Okay.
but the Laplacian conjugated. So this thing here. And here we can work in, I mean, the norm operator in L2, L2. I mean, the original paper is with L2 with weights, but so here the point is that, I mean, this decreases with the modulus of theta. And this is, I mean, this is the key point. While in the subsequent results, something like that was not happening. I mean, different spaces were used, and actually spaces were used in such a way that the norm of this operator was 1. But then somehow the gain, I mean, at the end, what we need is that Q understood as a multiplicator operator times this inverse is smaller than 1 in order to make the inversion. Or this is one way we can do it. So we need that this product, I mean, the norm of this whole operator is smaller. Here we get that because this can be, I mean, the norm of the second operator can be done arbitrarily small. In other situations, what it is proof is that in some spaces which depend on theta, on the vector, this Q has norm arbitrarily small, or in some sense, or in some sequence, and then this has bounded norm.
Right. Sorry, last question.
Sure.
Indeed, the topic is very interesting. I think it was slide 11. And that was about your contribution, right? Because you mentioned that you have this kernel that probably was with these two functions, these two exponentials, harmonic in Y, right? And you mentioned that you managed to have an analysis for this function that was actually your contribution to the topic, right? At some point you mentioned this.
Well, not only, I mean, I added the team. I was added to the team. I mean, it was not my contribution on my own. Yeah, so the point is that what they were, I mean, roughly speaking, this K here is the, I mean, what they were using was, I mean, in order to invert this operator, to use the FADEV fundamental solution. So let us write this in Fourier, and then we consider, I mean, we invert it, and okay, it's necessary to check that everything works well, but this is more or less the idea. But in the result of uniqueness for Lipschitz conductivities, they were not they were not using I mean, this explicit fundamental solution in order to study this operator. They were not using that this was a contraction. And somehow we were going back to the previous idea, but again, I mean, having less regularity imply to use like more technical spaces than the ones used, I mean, with more regular conductivities. But I mean, somehow if this is, I mean, I mean, if this is the good, I mean, like something explicit, is not, I mean, this is the fundamental solution of this operator here, right? So then, I mean, and then we are conjugated, so it can be not very, I mean, quite directly, it can be seen quite directly that this is harmonic, provided this is nothing too weird. And the point is, okay, be sure that this is not too weird.
Thank you very much for your kindness to answer these questions. Thank you in detail. Congratulations for the talk.
Thank you very much, and sorry for the technical problems I had during the talk.
It was amazing. Thank you. Okay, thank you very much. So we are going to resume in 45 minutes, 45 minutes with the talk of Professor Luis Seco. Professor Pfefferman, are you there? Professor Pfefferman, can you hear me?
Hello, 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 hello,
Hello, Professor Pfefferman, can you hear
hello.
me?
Yes, yes, do you hear me? Duvan, hello.
Hello, Professor. Well,
Oh, oh, Okay, we connect. Thank you. That wasn't easy. Thank you very much. Okay, my co-host has asked me to start my video, says Zoom. I will start my video. I don't know what it means.
Right. I think that it will help you to activate your camera
Okay.
to see that your camera is working
Oh
well.
yes, my camera is now working. Okay, I will simply stay logged in from now until at least my own talk is finished. Okay, I won't be here, but
Thank you
I
very
will.
much.
Oh, thank you. Okay,
I,
okay.
I am glad that you were able to connect. And just in case if you want, we are now in break time,
Okay,
and if you want
okay.
to make a proof or something, you want to share slides,
Oh,
we can do that proof now if you want, or later.
um, all right. Let's see.
I can
I
wait in any case.
Oh,
Okay.
all right. I will be all right. I'll put the computer away, but stay logged into Zoom, and I will be back in maybe 5 minutes and get my slides up. Okay.
Sure, Professor. Thank you very
All
much.
right. All right. Thank you. Wow. Never a dull moment. Okay.
Yes, sure.
Okay. Now, let's see. There's that. I don't dare get out of that, but I can. Let's see. Let's move that. Maybe if I do that. There go. Okay, very good. Okay, we cancel that message. Okay, now we search. Okay. Mhm. Um, okay, let me see. Duvan, am I able to share the screen?
You are not able to share your screen, Professor?
No, I'm asking. I haven't tried yet.
You are able, yes,
Okay,
because
great.
actually you have the co-host
Oh, okay, great. All right.
permissions
So,
option.
okay. So, all right, I'm going to share the screen and it should be, wait a minute. That's no good. Let's see. Desktop 1. Wow. Come on. There. Share. Okay, and now if let's see. There. Okay, there's the first slide. Do you see
Yes,
it?
yes,
Okay,
Professor Pfefferman, I see intrinsic manifold learning.
great.
That's
Okay,
great.
okay.
Thank
All
you
right.
very much.
Oh, please. All right. Thank you. I'm sorry that this was trouble for you. But I think now
It's
the
our
problem
great
is
pleasure.
solved. Okay, thanks.
It's our great pleasure.
All right. So let's see. I believe, right, I'm talking at 2 o'clock my time, and I will be back, let's say 15 minutes before that. Okay?
Thank you very much. Next talk will be by Professor Luis Seco, actually your PhD
Oh,
student, former PhD student,
oh, oh,
Luis
oh,
Seco, next week.
oh,
Next talk,
oh,
Luis Seco.
when does he talk?
Actually, is the next talk. It will be in half an hour, more or less half
Oh,
an hour. He
all
will be
right.
here.
Oh, okay. I will I will watch it unless
Yes,
something goes wrong. Oh,
yes,
okay. Oh,
you're
great.
here, you're
Okay.
welcome. And
Okay.
also, Professor Antonio Cordova gave his talk a couple of days ago. And okay, maybe I will share with you the link you were
Oh,
mentioned
oh,
during his talk. That was,
I would I would love to see his talk.
thank you very much.
Okay. Oh,
Okay,
thank you.
Professor.
Okay.
Thank you.
So, all right. So I'll be back in half an hour or so.
Thank you very much, Professor.
Okay, great. All right. See you then. Thanks.
See
Bye-bye.
you, Professor.
Bye.
Professor Luis Seco, can you hear me?
Yes, I can hear you. Can you hear me?
Yes, Professor Seco. Thank you very much for joining us and for accepting our invitation. So Professor Charlie Pfefferman will be connected actually for your talk.
Yes, I can see him there too. Yes.
Yes, good. Do you think that maybe sharing your slides to make a technical test will be convenient?
Yes. Okay, you need to allow me to share.
Okay, I see. Please let me see.
Still not.
Okay, it's just a couple of minutes.
No.
Okay, well, Professor Seco, can you please check if you can share your screen? Wow, nice background. Okay, good. Do you want to try
Okay.
to see if you can move your slides? Because I can see the title actually. Very good. Excellent.
Good.
Okay, thank you very much. Are you in Toronto now?
No, I'm in Vienna.
Ah,
And I'm leaving for Milan right after my presentation.
okay.
I will try to stay for Charlie, but I have to be in Milan at 10 in the morning, and I'll have to drive through the entire night. There's only one way to go from Vienna to Milan with this
Yes,
time constraint, and this I have to drive.
right. Good. We can also share with you the link of the talk of Professor Pfefferman in case. Okay, good. I think we have enough time. We are 15 minutes before your talk at this moment.
Yeah. In fact, I just finished giving my talk at the conference I was at here, so I
Yes,
had to
thank
rush
you.
from the conference center to my hotel room. So
Thank you very much.
okay.
Okay. So in 10 minutes, I'm going to come back. Okay, thank you.
Very good. Yeah, I will unmute. I will mute myself now. Okay.
Thank you, Professor. Hola, Elder, ¿cómo estás? ¿Me
Hola,
escuchas
Duan,
bien?
¿qué tal?
Excelente. Elder, muchas gracias por aceptar ser chair en la sesión del profesor Pfefferman.
No, con mucho gusto. Felicitaciones por todo el trabajo que estás haciendo. Muy bonito todo. Me he podido conectar a algunas charlas y todo muy bien. Así que felicitaciones, Duan, por ese trabajo que estás desarrollando ahí, ¿vale?
Muchísimas gracias,
Voy
Elder.
a cambiar por acá el nombre mío para que no tengamos dificultad y ya pues estamos conversando. ¿Listo?
Sí, just one question, Professor Seco. Are you connected with two devices?
I am connected with two devices, yes.
Very good. Okay. So do you
My
need permission
iPads,
to, thank
yes.
you. Do you need also permission to share a screen in the other device?
Let me see. I like to use my iPad to make annotations if needed. I'm going to check if that works, okay?
Okay, Professor.
Everything works very well. I can make annotations on my iPad.
Okay, Professor, thank you. Listo, Elder. Eh, entonces todo está bien, Elder, creo. La charla del profesor
Sí,
Pfefferman.
sí, 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 creo que sí. Entonces, una vez que el profesor Feferman vaya a iniciar su presentación, entonces, imagínense, me darás la palabra y yo hago la introducción. ¿Te parece?
Excelente, profesor. Entonces a las 6:55 le doy bienvenida a la audiencia y te paso los share duties a ti, ¿vale?
12:55, ¿no?
Sí,
Listo, está bien.
muchas
Perfecto.
gracias,
Igual yo voy a asistir
profesor.
a la charla del profe Seco, entonces voy a estar ahí conectado.
Listo.
Bien, bien. Muchas gracias, Juan.
Tengo una pregunta, Dugan.
Okay. Okay, let us start them.
The talk is how long? It's scheduled for an hour.
It's scheduled for an hour. Essentially, you can take, if you want, 50 minutes plus 5 minutes
Okay, good.
of questions.
Yeah.
Okay, very good. So, dear participants, ladies and gentlemen, it's my great pleasure to welcome you to this session and to introduce our distinguished speaker, Professor Luis Seco, who joins us from the University of Toronto. Professor Seco is a globally recognized leader at the intersection of advanced mathematics and real-world applications. He is a professor at the University of Toronto, where he directs the Mathematical Finance Program and is the founding director of Risk Lab. In addition, he serves as the chair of the Center for Sustainable Development and the Fields Institute. His expertise lies in mathematical finance, risk management, and sustainability, where he has built an outstanding career translating sophisticated mathematical theories into practical solutions for industry and society. What truly distinguishes his work is his commitment to bridging the gap between rigorous academic research and practical problems arising in mathematical finance research. Today, Professor Seco will present his lecture entitled The Mathematics of Sustainability. So, Professor Seco, thank you very much. Please go ahead.
It's a wonderful opportunity. I was thinking what to cover, and I decided to make this talk to be a little bit autobiographical. I'm assuming I have an audience of mathematicians, and for a long time, I've been involved in different ways in which mathematics finds its way into the world outside of academia. I started my career with Charlie Pfefferman at Princeton, that you're going to be listening to right after me, and that was a wonderful experience, a 10-year career working on mathematical physics, after which I moved into finance. And I spent about 20 years working on different areas of finance. In fact, I managed money at an asset management company. And then something happened, which is how my story starts today. Something happened during COVID-19. My story starts with COVID today. So the year was 2020. We were in the midst of the pandemic that we all suffered. And around the month of June, I received a phone call. The situation in Canada was as follows. Health is managed by the provincial authorities. We have provinces in Canada. And there was a committee of scientists, most of them epidemiologists, but there was one mathematician in that committee, and that was Kumar Murthy, the director of the Fields Institute at the time. And they had been doing some modeling on the pandemic and advising the government as to what they should do in terms of closing restaurants, opening schools, or all those decisions. We call them intervention measures. And around the month of June, there was almost something like a civil war inside the government. The Ministry of Health was having a big battle with the finance ministry. The Ministry of Health wanted to close everything, and the Ministry of Finance was saying, we're going bankrupt. We can't do that. So we need a balance. I was a mathematician around the corner who knew about money. So I was asked to give an opinion on money, on the situation dealing with the pandemic. And I was warned. I was given a call on a Monday, and I was warned that they wanted a solution by Wednesday. And I know the real world. I've managed companies. I know that sometimes you need solutions yesterday. Tomorrow is even too late. But I missed that Wednesday. But by the following Wednesday, we had a very interesting model. I gathered my best 3 graduate students and we produced a model, which is how I started this adventure into the world of sustainability that I want to tell you about today. Now, but before I tell you the model, and I would like to give you a fair amount of math, because I know I suspect this is what you enjoy, but I want to start with this picture that I have here. It's a picture of the Premier of Ontario. It's like our governor, Doug Ford. And this is a picture that he has a press release every Thursday. That's why we had to provide some numbers by every Wednesday. And that's what we did. For a year, we met every day at 6 p.m. And then on Wednesdays, we produced a report that eventually went to the Premier's office. And in this particular press conference, he displayed one of our graphs. And I feel very proud of this because it's a very good symbol of how when you do a mathematical modeling of something, sometimes it actually has impact. So I like to start my story with this picture. I would like to think that we had a contribution to the improvement of either the health or the finance or both in the province of Ontario. and for me, this was an overture into a new paradigm for myself. Like I said, I had been writing papers, I had been an academic, I had managed money, I ran a company. So the world of academia and the world of industry was not unknown to me, but the world of government and policy, that was new. And I started with this, essentially with a picture that you see in the hands of the Premier of the province of Ontario. Now, what is that? What I was asked to do is I was asked to provide some financial considerations to a health analysis. The first thing that came to mind is something which is very well known in finance. Harry Markowitz in the 1950s, came up with a very interesting model for portfolio management. His model was the following. Up until 1950s, investing was buy the best stock at the best price. So it was a one-dimensional decision. Markowitz made it two-dimensional. What he says is, yes, we want a good price and a good return, but we also want to worry about risk. So he introduced a new element, the element of risk. Now, he did that in 1952. In 1951, the first computer was created at the Institute for Advanced Studies at Princeton. So if he had said this 10 years before, maybe no one would know. But he said this at the time when the concept of risk could finally be implemented. It's not something that you can do with a calculator. Fortunately, we had computers just invented 1 year before. He was at Stanford, by the way. He was not at Princeton. But then his theory became very successful. And to this date, people still talk about the Markowitz framework in finance. And in his framework, what he does is he has 2 axes. In one axis, he has the good thing, which is return, financial return. And on the other axis, he has the bad thing, which is risk. And then he says, everything you do is on a plane. So let's optimize your decisions looking at a plane. Now, it's an extreme example of information compression. The world of investing, which is very complicated, is now being mapped into a two-dimensional space. But in the 50s, that was fantastic. It introduced a new element that could be managed. So I knew all of that. Everybody in finance knows all of that. If you don't know finance, I invite all the mathematicians listening to this to please learn, because that's fantastic. This thing that Markowitz did in 1952. By the way, he died shortly after we did our model. Okay, about a year after, and sorry for that. But what we did is we did the same. You say, why, if his model was successful, why don't we do a model in which I have the 2 ministries that were at war, the Ministry of Finance and the Ministry of Health. And then I model each of them independently, and then I put things on a plane and see what happens. So what we did is we looked at the Ministry of Finance. We had the finance access. And we benefited from a lot of work done by a lot of people that had very good analysis already done as to how school closures, restaurant and retail closures, and so on and so forth affects the economy. We didn't have to do it. That model was already there. And then we took the simplest approach because we had to finish by Wednesday and it was Monday. So we took a linear model, and a linear model which is with betas, to model the impact of those variables into the economy. And the result is, well, let's do the simplest thing that we can. Every time I make a decision, it has impact. We took 5 variables that you can see there, or, masks, mass gathering, this and that. And then that has an impact on the economy, and people knew that. We focused at the beginning on the impact on unemployment. So we just came up with the simplest economic model, linear, as a function of what? As a function of the decisions that you make. Now, that's the key. This is very hard now. Although the formula is very simple, the model is as follows. Decisions are made weekly. So you make 5 decisions every week, and then you change the next week. So that's a space that very quickly has a very big dimension, right? We were projecting what's called case loads, which is how many people get sick a year forward. Okay, so that's 5 variables per week, 52 weeks in advance. So that's a lot of variables, but that's okay. Let's just write that down. And that's what we did. That was how we modeled the financial impact of the decision of the government, whatever it is. We lived in a space of very high dimensions. Then we went to the health axis and we dealt with the Ministry of Health. And there again, we used models that epidemiologists had developed. We didn't have to do them. And they had ways of finding impact of how these things work. Let's not get into that. And then I can say, well, Mr. Government, if this is what you're doing, this is your choice of mask mandates, mass gatherings, week after week, your policy is here. We could say that. Okay, so we had a 2-dimensional representation of a policy made by the government. And it's very important to say that this is not the policy they make today. This is the policy they make today, thinking that they will change next week and the week after and the week after. Okay, this is what in mathematics is called stochastic control theory. Every time you make a decision, it's how you play chess, right? So for every possible move that you have, the virus will make its moves. And then I can tell you that your policy is here. We could do that. We could calculate that very efficiently, very quickly, thanks to the work of a lot of people in economics and a lot of people in health. And then I just simulated all the possible decisions that the government can make. And the picture that you have on the screen is the result of those simulations. Now, this is where mathematical thinking becomes to be very important, because if this is your policy, I can tell you that you can improve your policy in 2 ways. You can have an improvement keeping the caseload constant, so number of sick people constant, but having a positive impact on the economy. Or you can say, I'm going to keep I'm going to decrease the caseload, keeping the impact on the economy constant. I could make those 2 improvements. Now, very important to say here, I did not get into any other decisions. Public policy is a very tough job. In this particular case, you have to actually calculate the value of a human life. That's what this amounts to. We didn't have to do that. We were able to optimize decisions, keeping the number of sick people constant or keeping the financial cost constant. That's a strict improvement. We only have 2. Any other decision on that is called efficient frontier, on that boundary. Every other decision, that's for the policymaker to make, not for the mathematician. We didn't do that. We just offered this. By the way, this is a very interesting picture, because in this picture you can see how the different countries took different decisions on COVID. For example, Sweden. Sweden cared a lot about the money and not so much about the sick people. So they were on one part of that boundary. The United States, they cared about one thing at the beginning, then they changed. So they moved from the, all over the map. China, same thing. They care a lot about the sick people at the beginning, and then finally they had to open up in 2022. So you could put all the public policies, not just of the government of Ontario, but the whole world on that map. Of course, the parameters are for a specific province or for a specific country. So this was good, and it was understood by the policymakers, and we could help them improve their decisions. And it's something which we did this in a week and a half, and then every week we had to do the constant update and the corresponding advice or decisions that would come as a result of that. So this is this is what I did in 2020. At the same time, as I was doing everything else that I was doing, I still had a company that I had to manage, and I had my PhD students. They had to write theses. Eventually, they wrote theses on this, but this is something that I did, and it got me thinking. It got me thinking because I thought this is a very interesting way in which mathematics can have impact. And then after the pandemic was over, it occurred to me, so if the pandemic created this, what would the next emergency look like? And I started to think, what would that be? And again, like I said, I know finance, I know companies, but this was different. And then I learned, and I'll tell you how I learned this. I learned about the 17 Sustainable Development Goals of the United Nations. These are objectives that 193 countries stated that is important to them. 17. You can see them here. No poverty, zero hunger, good health and well-being. That's what I did with COVID, okay? Quality education, gender equality. And then it occurred to me, so why don't we think what the next emergency might look like and get ready for that? So, and then one idea I had, and it's just an idea, is imagine we are like in COVID times, we're all asked to stay home, but at the same time, we're asked to turn the heat off. That's a different decision, right? And then are we ready for that? It became clear to me during the times of COVID that we were not ready for that. So then I started to learn, and I'm sharing my story with you. I started to learn about the Sustainable Development Goals, and I went from one to the other, trying to think how math could have an impact on that in the same way as we had impact in the case of COVID. Looking at this from the lens of an academic, we like to solve problems before they become real problems, but also with a commercial perspective in mind, because if you want to have impact, it's not enough to write a paper. It's not even enough to send a report to the government. Someone needs to do something. That's what companies do. And I had that expertise too. So this became the plan for my life in the year 2022. As a mathematician with experience in the industry and suddenly developing relationships with governments. So I started with what I consider to be the simplest of all of these 17 Sustainable Development Goals, emissions. And the reason I think it's the simplest, I mean, to say that climate change is the simplest of these 17 sustainable, well, what does simplest mean? Well, the thing with emissions is that it's a single risk factor, okay? Everything else was complicated. The virus was very complicated. We didn't know what it depended on. Our model depended on 5 variables that changed every week. But emissions is CO2, essentially. It's methane, but if you simplify emissions, it's a one-factor model. So I don't think it's the most important SDG, by the way. I think the most important SDG is probably water. Okay. In fact, the word water appears in 2 of them: marine life and water over the surface. That's the one that we need to survive, to drink, right? So, but I left water for later because it's too complicated. Biodiversity is fantastic, but that's extremely complicated. So I said, let me look at emissions. And I started looking at emissions. And so I don't know how much of this you know, but it's important to understand that what's climate change about? Climate change is based on the following thing. There's a lab experiment that I should say something. They call it the greenhouse effect. I actually don't like the term greenhouse. I like the term microwave effect. Everybody has used the microwave. We all know that when you put food on the microwave and you press the button, the food gets warm, but the plate does not. And why is that? It's because those microwaves have been calibrated to interact with water. They make water particles spin, and that's why food gets warm. But the plate has no water, so the plate does not get warm. So something very similar happens to the Earth. The sun rays, actually the reflected sun rays, they create some microwaves that interact with certain gases. Oxygen doesn't care. Nitrogen doesn't care. CO2 cares. CO2 is a molecule like that. And then when it's hit with those microwaves, it starts to spin, just like the water in the microwave. Makes it hot. And of course, if that's hot, then everything else around it is hot. Methane is another molecule. It is carbon and oxygen, 4 of them. And then that spins even faster, 80 times faster. Okay, these are lab experiments. So the implication is that we think that then the atmosphere will get warmed up, and that's where we want to decrease emissions. Now, the precise relationship between the fact that a molecule gets warm and the whole Earth gets warm is very complicated, because there's one greenhouse gas, in fact, one of the most potent ones, which is water, H2O. But water is not a concern. No one cares about water in the atmosphere because it rains. But CO2 stays there for 100 years, and that's why we worry about it, right? So it's a very complicated issue, because also we know that as the temperature gets hot, we get more clouds, and the modeling of that is very complicated, and wonderful people are working on that. That's a very difficult problem, and I wanted a simple problem. So what I did is I learned what was done in Kyoto in 1997. In Kyoto in 1997, for the first time, they realized that if you want to solve any problem, you need to bring money into it. That's how we work. So Kyoto did something very interesting in 1997. They said, we're going to make an attempt to decrease emissions. That means that those who decrease emissions will have to be paid by those who do not. One of the original arguments was Brazil. Brazil has the Amazon. The Amazon is a big carbon sink for the world. They take care of a lot of carbon capture, but they do it for free. Wouldn't you say that we'll have to compensate Brazil for what they do? I don't know if you have people here from Brazil, but you need to introduce a way to compensate carbon capture if you want carbon capture to happen. So what they created is a very interesting notion. It's just a notion, which is, why don't we have an exchange of money between those who do carbon capture and those who do carbon emissions? Now, when talking about this is my home turf. This is finance. I know this. I've been working on this, and these are very interesting markets. And I should say that, by the way, last year, the Securities and Exchange Commission declared that this is a derivative. When that happens, you know that this market is going to grow. So these are the financial markets of the future. And I found it to be fascinating, and how you can create exchanges where carbon is bought and sold. And this is happening today around the world. I'll tell you more about this. But to understand the practicalities of that, I want to share with you 3 business cases very, very quickly. Okay, you will understand how math can become very, very relevant in this situation. Here's a case, I like it very much. It's a case that happened in Kenya. It actually has to do with water, because there was a company, a Dutch company, that produced water filters for 4.5 million people. And in Kenya, before those filters, if you want to drink water, you have to do what's on that picture. After their filters, that's all you do. And someone has calculated that this saves approximately 2.7 million tons of CO2 per year. All right. How do you calculate that? This is not so hard to do. This is not so hard to do. But the interesting part for me, because you know how much water is drunk, you know how much wood is typically used, so you can make this calculation. But this is what's interesting. Once you bring finance into this, like in the case of COVID, 2.7 million tons of CO2 is how much? Well, it depends on the market. In Europe, that's about 200 million euros per year. In the United States, it's about $100 million per year. In China, it's about $30 million per year. Depends where you are, because these markets exist. This introduces a cash flow attached to the activities that we do as humans, and introduces a very interesting layer of accounting that needs to be done when we do anything that either absorbs or emits CO2. Okay, so that's one. Now, that's not as interesting as this next one. The next one is this is one of my favorites. This is a tribe in the county of East Kimberley in Northeast Australia. It's the Nyaliga tribe. They are in the Australian savanna. The Australian savanna has a very big problem with fires. By the way, we all have problems with fires. Toronto was unbreathable yesterday because of again, fires and how. So they have that problem in Australia. So this tribe is paid money to burn the savanna every year. How does that work? So that's where this tribe is. And what they do is they do controlled burning during the wet season. If fire happens, and they do happen, during the dry season, they're horrible. They burn at scale for a long time and tremendous damage and a lot of emissions. But if you do controlled burning, they have seen that 33% of the area burns, 33% less of the area burns, is good for grass and wildlife. But what's most important from a financial perspective is that 40% less emissions. And this translates into real dollars. Now, let me tell you, this is what I tell my students when I get to this particular point. How is this calculated? Now, this is no longer easy. This is no longer easy. What I want to do now is I want to show you some screenshots from some of the documentation which is required by the government so that this company can be compensated for that carbon capture. This is a report of about 200 pages. It takes several months to make. It's made by humans, taking samples on the field. And then it's written by humans. So what I tell my students is, this is something that could be done by computers. And I'm going to show you how this is done by computers now. Okay, this is one of the things that we do in one of my companies, a company we created this year in Spain. We take satellite pictures and then we can calculate these things directly from data which is given to us. And this is interesting because everybody today is used to trading a stock on their phone in a second. But when stocks were invented, when the first stock exchange in London was created in 1701, trading a stock was very complicated. And in particular, you had to do a type of accounting very similar to what you have on the screen now for carbon capture. So as a way to get ahead of ourselves and try to understand all these things, maybe this is something that should be automatized. And here is one way to do that. This is an app that has been developed, and we actually did the launch of this just about a week ago, where you pick a location, you pick, in this case, this is for forestal development. You pick a forest, what tree you're planting. And then I give you a cash flow over the next 25 years that you will collect because of the carbon you're going to be capturing. You can do this, we can do these things now. Humans are able to do these things now. This means that I can value a forest financially and accurately, and not because of the price of wood that I will sell. No. This is the value of carbon capture going back to what Kyoto did in 1997. These are the new financial markets that are developing. And mathematics is key to be able to make these things happen efficiently, quickly, and reliably. But this is the science of today. But I want to mention another thing, which is actually what really got me for the first time in 2022 when I started to look into this. I have here a table, a very well-known table. The table changes every year, but it's almost always the same. And it's a table of emissions by country. And everybody talks about the same thing. China is the biggest emitter. They have 1.4 gigatons per year, right? Then the United States is number 2, and India and Canada is number 7. Okay, according to these numbers that we have here. And this is the first time I looked at this, I mean, there's an obvious comment to make is, I mean, you're comparing, I would not say apples and oranges, but you're comparing a country with 1.4 billion people with a country like Canada with 40 million people. So it's the wrong comparison. So what people do, and this is interesting, what people do is they divide and they calculate the emissions per capita. Actually, it's interesting when you do that, Canada is number 7. Again, it's a fixed point, okay? But of course, China disappears because their emissions per capita are actually not so high. But then what happens? Well, countries with very small populations show up, like Canada, okay? So the conclusion, any mathematician who looks at this knows that both these tables are meaningless. The absolute number is not what matters. Neither is that number divided by the population. The population is just one of the factors, but there could be others. Like, for example, the surface area, right? But most people cannot understand this. And by the way, I should tell you that the Paris Accord of 2015 was based in these arguments that I'm telling you here. We had lawmakers talking to each other, negotiating, arguing, fighting with each other when they didn't understand a single number. Because this is not the way to understand these numbers. Here, I like to, there's a wonderful quote by Paul Erdos that I think all mathematicians should know. A mathematician is not someone who knows how to add, but someone who knows when to add. And mathematicians would know, in this case, I would have to say divide, right? Mathematicians will know that neither looking at that table nor the division is the right thing to do. So what is the right thing to do? So this is something, I'll just give this a result that we did to give you an idea that this is something which is highly non-trivial, is to understand what causes emissions, how emissions are a function of what. And what we found is that there's a number of factors that explain the emissions. So it's not a matter of dividing by one factor, it's not a division. It's some sort of a regression that you have to do. Or maybe a more complicated, we have to use a nonlinear function to be able to map that. And the result is very interesting because once you do that, and I don't know that lawmakers will understand this, but once you do that, you can do the following. I can give you a baseline for what your emissions should be based on your country parameters. And then I look at the difference between your true emissions and your baseline. And then you have countries that are becoming browner and countries that are becoming greener. And we do this by doing peer comparisons. No emotions, just data science, okay? And again, another area where mathematics can have impact. And you see, as you can see, the themes that we developed during COVID keep coming back. And at every one of these themes, you have to pick up non-trivial mathematical problems that you have to figure out a way how to solve as well or as best as you can, okay? But now, the next topic I want to discuss is, we're going to discuss sustainability is, okay, if you want to have impact, what should you do? Explaining numbers is great, but now what do you do? And to be able to do that, you need to have a different way of thinking, completely different way of thinking. And I want to start with two, I don't know what you think of Steve Koonin, but I like to use him as a way as a way to explain something else that math is good at, which is the logic behind the numbers. Okay, so I have two quotes by Steve Koonin. And again, I mean no disrespect to Steve Koonin, but he said these things, so they deserve a comment. So first, Steve Koonin argued in his book Unsettled that increased carbon dioxide contributes to a greener world. And he's right, because it is true that CO2 is plant food. In fact, there is a conjecture that photosynthesis probably developed randomly, sporadically, when CO2 levels were about 10 times what we have now. We don't know. So this is true. So from a causal perspective, it is true that CO2 causes tree growth. It's true. But it also causes other things, which are not so good. So whenever you try to do policy, you have to be fully aware, not just of one edge in your causal tree, but aware of the whole tree. So that's the first thing. Now, my favorite statement by him is this one. He said, high emissions solve hunger. And the reason is, he says, the 20th century has witnessed the biggest increase in CO2 emissions and global food production. So CO2 is good to remove hunger. Now, what's interesting here is, I just give you a causal graph. If you look at these two numbers and you do look at the correlation, yes, the correlation is positive. So what? The correlation between going to the hospital and dying is positive too. That means if I'm sick, shall I stay home? Well, so let me tell you about that, because I can complete, I mean, I just made this graph myself. I don't know if it's accurate, but if I want to understand, hunger has been reduced by a number of developments like engineering, agromechanics, of course, increased food supply, but also increase in transportation. And these things are what caused the increase in CO2 emissions. So it is not true that if you increase CO2, hunger is going to be solved. No, hunger is solved by something else. And in causal logic, these things have a name. These factors that affect two factors at the same time, they're called confounders. And you cannot find confounders by doing correlation calculations alone. It does not work. So this is not logic. We need to have proper logic. So what I'm discussing now is how do we do this? So we do this with a graph theory. Graph theory, in particular, a specific type of graphs. They're called directed acyclic graphs. Directed means because A implies B. We know in which direction this graph goes, okay? You have to go that way, not the other way. You need to know what causes what. And they should have no cycles. Sorry. A cycle, a cycle is a tautology. This implies that and this implies that. No, it cannot be. I need to have independent factors. Sorry, not independent. I need to have factors which they are logical. If this implies that, this cannot imply this. I cannot have a cycle in that graph. And then there's a terminology in terms of a descendant, things which are implied by others, an ancestor, thing that implies others, and so on and so forth. So the key to having impact is to understand this graph and to do something with it, okay? And once you know the implication, then you could do correlations or graph weights or things like that in as many factors as relevant. And by the way, I rate correlations, but you can do random forest, you can do whichever functional dependence is appropriate for that particular factor or edges, okay? And the way we do that, and I'll be very fast with that, is we do it as a two-step. The first thing that we do is we do what's called the establishing the causality. And right now we do them with large language models because business as usual knowledge, status quo, is good enough to understand this. Okay? So that means I just need to know if my weight is +1 or -1. I'm going that way or this way. I don't need to be very fancy when it comes to that. The fanciness comes on the statistical inference part, when I can give weights, precise weights to my graph, and I know what's the impact of different things on what matters to me. Okay? So I have a very interesting application here on hunger, SDG number 2. You may have heard someone made a calculation that if countries donate 0.7% of their GDP to poor countries, we solve hunger. All right, well, that's not true. And let me, again, without doing the full graph, let me show you why that is not true. Population growth, as you know, is a function of many things. It's a function of not just lifespan, but birth rate and other things. So if I improve some countries' lifespan, keeping the birth rate as what it is, I get an explosion in finite time, right? However, if I understand what other factors affect, for example, if I have an idea of how education impacts a birth rate, and I just made up this linear regression here. This is just for educational purposes only. This is not meant to solve any problem, okay? It's just a way of thinking. Then I can do the same thing with health and lifespan, and then I can see that if I just increase the lifespan without modifying the other factors, I have a blow up of population in finite time. But if I can control the other factors, then I can have a good sustainable population growth, knowing that population have to share the resources of that particular country or community where they live. You cannot extinguish those also. So this is an example of how to do things in this way. And so the road through causality goes through basically 2 stages. One is to understand A implies B, and there you can use all the math, all the traditional math that we have, but then you need to understand the whole graph, not to make the mistakes that Steve Koenig makes, for example, in his statements, okay? And I have some examples here. I come from finance, so these are things that people in finance will understand, but let's get away from that. This is the first result that we obtained. We did an analysis of credit risk. Let's just look at the graph, ignore this. We did an analysis. This is very interesting. It probably happened to you. Years ago, when you apply for a credit card, you fill a form that essentially has 5 pieces of information about you. And then banks decided to give you a credit card. Today, it's not like that. They know everything about you. They know how much milk you drink, because they get that information from the supermarkets. The biggest supermarket in Canada owns a bank. So it's important to understand anything, in this case credit, from the point of view of what implies that. Okay, so the analysis of confounders is very important. Traditionally, causality is defined as follows: the probability of B conditional on A is bigger than probability of B, then we think that A has an impact, right? But then if you look at the probability of rain, if I look at how many umbrellas people carry, it would lead me to believe that umbrellas cause rain. We know that's not true. We know that when I carry an umbrella, it doesn't rain. It only rains when I don't have an umbrella. Okay, so we need a different way of doing this thing. So we need to have and this is something which is fairly modern, I would have to say, because this is something that is linked to the concept of interventions. To be able to conclude this, I need to take 2 populations, and then one carries an umbrella, one doesn't, and then I do the statistics of that, and only then I will know if these things actually have impact, right? And all of this, I'm not blaming Pearson, but the Pearson correlation in 1896 was favored so much because it was so easy that it ignored. It was used everywhere. We used it. I mean, Markovits that I mentioned earlier, correlation is what made him famous, right? So all of this has led to the decline of causal reasoning. Understandably so, because data was very scarce up until now, and it was very hard to do anything else. But today, that's not the case anymore. We have a lot of data, and what I see happening, and this is an announcement I want to make, is I see the opposite. I see it now is the rise of causal reasoning that maybe started very feebly with Judea Pearl's work on causality in the year 2000. Okay, it allowed for the creation of interventions to understand, for example, the effect of some medicine on a treatment. And I think it was perhaps the grand opening of this was with the Nobel Prize given to Guido Imbens and others for precisely doing that, randomized trials. And I've used correlations all my life in everything that I did. One of the papers that Charlie and I wrote was about electron correlations. So I would be the last person to say anything bad about correlations, but today we can do better than that. When it comes to sustainability, we can understand what causes what, and introduce some sort of interventions. Okay, this I explained the dual operator in the context of umbrellas and rain, which is very easy to understand. You take two populations, one with umbrellas, one without, and you do your statistics. In the end, you get that. The result is, as we know, umbrellas do not cause rain. That's how you do it. Okay, with the dual operator with interventions. If you could do that in other areas, then you will have a proper graph and you can do something about that. So what I have here is, I'm just going to show you the graph. I'm very proud of this graph. This is the graph of emissions. Please don't ask me anything about, it's not important. What the important thing is that at the bottom, we have emissions. And in the middle, we have everything else that we can control. So for example, this fallacy that says that to decrease emissions, we need to become poor is false. There's many things there that allow me to decrease emissions and still increase my GDP. Okay? There will be things that I can control, but this is a very complex system. And if I understand the system, then I can do something. And this system is very complicated to build. This is where you need a lot of math. Every one of those edges is a mathematical problem in itself. And the creation of the graph where I only know what implies what is perhaps not a math problem, but it's a logical problem in itself. A problem that we know. We know that if we increase heat, we're going to consume more. Things as simple as that. Okay. So for me, this is a graph of hope that if we understand what causes what, then we can intervene. And this is better than, like I said, this is better than COVID-19. In COVID-19, we had no idea if masks were relevant or wearing gloves was relevant. These things are much better understood. So with some with some math, we can do wonderful things. And I want to end my talk by telling you how much we will win if we get this right. There's a calculation that I don't know if you have seen, which I encourage everybody to do. I do this with my students in great detail. There's a constant, which is the following. The energy we get from the sun is about 1 kilowatt per square meter. It's a physical constant. You just calculate, okay? A solar panel is able to absorb maybe 20-30% of that. So I'm not talking about the electricity we generate from a solar panel. No. I'm talking about the energy we get from the sun on Earth is about that. So let me do a calculation. I have here the GDP of India, Germany, China, $20 trillion, United States, 30 trillion. This is the GDP, this is the value of all the gold in the world. Not only the gold we extracted, but the gold which is still on the ground. This is the value of all the oil in the world. By the way, that's why we have wars. A different causality. That's the value of the electricity, energy we get from the sun on a given day. Per day, we get $400 trillion. If we are able to harness that somehow, that will change everything. There's one person who said this differently. Elon Musk just published a few days ago something which is, it's along these lines. It's based on the same number. Okay. No, we're not able to do this yet. But if this is something that we can do, this means we can multiply our energy consumption by a factor of 500 and still be okay. And I just talked about energy and emissions, but imagine what we could do with water. imagine what we could do with biodiversity if we are able to understand the systems which are around us, if we're able to understand poverty, if we understand the mathematical dynamics that drive those, the world will really change and everything will be different and better. Thank you very much. I'll take questions now.
Thank you very much, Professor Riseco, for, of course, this very interesting talk. So let me check if someone has expressed questions in the chat. Okay, participant says, thank you very much for the very nice presentations, they say. Actually, not questions there.
I'm trying to win people to work on this problem. That's what I'm trying to do. I'm trying to convince people that mathematics can really change the world, not in a philosophical way, in a real way. And only math, by the way.
Thank you. Thank you very much.
I
Now
have a
then,
question.
yes, actually, Brian Grajales is making a question. He says, is there any measure of causal influence analogous to a correlation coefficient? Is his question.
Okay. So the way causality works, so I went very fast through this, but for me, causality is A implies B. Okay. Once you have that, once you establish that fact, which perhaps is not a mathematical fact, it's a physical fact or a medical fact or something. Once you know that, now you give me data and I will make sense of the data. But I need to know that A implies B. If I don't know that, then the data you give me, I have no idea what to do with it. Very likely I will misunderstand the data. Okay. Right. I'll give you an example. If you don't know anything, absolutely anything about medicine, and in fact, look, people are afraid of going to the hospital. Why? Because they know bad things happen in hospitals, right?
Yes.
You would say good things happen in hospitals too, but that's not true. Good things happen outside of hospitals, right? In hospitals, most things that happen are bad. And people are afraid of that. Now, if you're a doctor, say, no, no, no. I mean, there is a confounder, which is you're sick. That would take you to the hospital. So conditionally confounder, given that you're sick, you better go to the hospital because those data sets, when you do the interventions of that, the conclusions you should go to the hospital. But it's very hard even for the human brain to understand that, right? And that's causality. Correlations only are relevant once causality is established. If not, they're gonna fall prey to whichever. I mean, hoaxes are real, right? And a lot of hoaxes are based on that. I can do correlations on things that are unrelated, and then it looks like because of what Pearson did, it looks like there's a relationship. There isn't. It's just a correlation. A correlation is you multiply numbers and the number is positive. Big deal. There are so many numbers that are multiplied and the result is positive, right? Causality is, you need to understand, you need expert knowledge of A implies B, and then correlations matter, only then.
Thank you very much. Actually, Professor Elder Jesus Villamizarroa is asking, how can artificial intelligence be integrated with mathematical models to optimize energy consumption and reduce CO2 emissions in real time, considering the complexity of interconnected systems and the need for evidence-based public policies?
Right. Okay. So this is a wonderful question. I have a whole course to answer this question, which I teach at the University of Toronto. Okay. And we talk about AI agents. And so let me summarize by saying the following thing. We live in a world where we're surrounded by data. Data that we're no longer losing. We find ways to harness the data. We have more sensors than ever before, and data is being gathered. We also are developing engines that can analyze these data sometimes in real time. okay? And then you can optimize decisions to be able to do that. Now, there's a term here talking about public policies. Why do we have public policies? See, public policy making needs to improve. They need to become expert systems. And right now they're not, because public policies in the countries that most of us live in, they have one objective, which is to win someone's election. That's the objective. And then a lot of the public policies are geared towards that. The objective is wrong. I'm not going to be the one saying anything against democracy. This is not about democracy. This is about making defining the right objectives for public policies to work. Public policy, how I started this in 2020 with COVID. We had a very clear objective: decrease occupancy numbers for intensive care units. That's what we wanted to do. Make it below 90%. Once you do that, you can develop agents that will consume data and help you optimize those decisions, oftentimes in real time. So it's a wonderful world that we can develop. We have the tools. We have the data. We have a lot of the knowledge. We have the goodwill. People are good people. They would do this if information is given to them. I think that we also have an issue, like we did with COVID, for example, of making sure people have the information. This is not just the data, the information, but we are in a situation where we could do that. Communications are better than ever, faster than ever. You can create, now I go into, you can create societies where information is established and exchanged very efficiently and with a modicum of truth. You could do that too. So this is the new world that we can develop. And it's based on logic, it's based on proper calculations. Back to my Paul Erdos, okay? It's a statement. You need to know when you add, not how you add. Computers add, but they don't know if they have to add or divide. They don't know, right? We can teach them through machine learning, that's what they do. But we need to start thinking differently, I think, in my opinion, about what we want. Define the objectives, these are the tools, this is the data, and just implement. Everything is an optimization system, right?
Thank you. Also, we have another question by Brian Grajales. He says, okay, maybe a silly question. He asks, given that correlations can be selectively interpreted or misused to support political, personal, or corporate interests, why do they remain so widely used in research?
Oh, okay. Well, they're used in research because they have meaning, right? Every researcher will tell you that correlations have meaning. And researchers that use correlations know what they are doing, and they know that sometimes they give you, I mean, they know the meaning. The meaning is not always the same. It could change, right? So, of course, we're going to continue to use correlations forever and ever and ever. They are fundamental, very useful mathematical concepts. But I think the question was slightly different. I think the question is really aiming at, given that people can take data and construe falsehoods with data, why don't we abandon something? Well, what I think we need is we need nonsense detectors. And I tell my students, the biggest superpower that mathematics give you is mathematics is the ultimate nonsense detector. I think with a lot of math, we will be able to filter out a lot of the nonsense. And I'm not going to say we're going to be right all the time, but I think the level of correctness in what we listen and what we understand will be dramatically better.
Okay, I think, okay, maybe I use the time for a final question of myself. You know, we have had emerging industries, right? Like the one of artificial intelligence in recent years that have developed large language models and so on. I wonder if in your research, have you considered the impact of these emerging industries for sustainability?
Yeah, so the answer is yes. In fact, that's what I do every day. I'll tell you, these industries that you mentioned, what they've done is they've made us more powerful. Sustainability is very complex. I started with emissions because it was the simplest problem I could look into, single risk factor. It's very complex. But now complexity can be attacked with these new techniques we have discovered. And that's why I'm optimistic. I'm very optimistic that the problems we have are greater than ever. But in a certain sense, those problems were already there. Now we are equipped with techniques that can help us solve them. And I'll say one thing, maybe to end, which is artificial intelligence is mathematics. By the way, computer science is mathematics. I mean, the von Neumann machine was done by John von Neumann. And that's the computer that was done at the Institute for Advanced Study, why it was called computer science. Okay, I think I know why, and I think that was a mistake, but that's a different talk, right? Mathematics is at the key of all the solutions that we can find today for the most complex, most pressing, most interesting problems we have as humankind.
Thank you very much. Thank you very much, Professor Luis Seco, for the very nice talk. Very inspiring, of course, for the ICMAM community. So now I will pass the chairing duties to Elder Villamizar, who will be the chair of Professor Charlie Pfefferman from Princeton University.
Okay, can I start, Professor Duan?
Yes, please, Professor Elder.
Okay, ladies and gentlemen, it's my great honor to introduce Professor Charles Pfefferman, one of the most distinguished mathematicians of our time. Professor Pfefferman works at Princeton University, one of the most prestigious universities in the world. His brilliance has been recognized internationally. He has received several distinguished awards, including the Fields Medal in 1978, the Salem Prize, the Berman Prize, the Wolf Prize in Mathematics, the Boker Memorial Prize, among others. His contributions to quantum theory, partial differential equation, global analysis, harmonic analysis have been truly extraordinary. His influence extends not only through his groundbreaking publications, but also through the many PhD students and collaborators he has inspired through his career. We are especially grateful with you, Professor Pfefferman, for accepting to share some of his extensive knowledge with our audience of the ICMAM Latin America Congress. Professor Pfefferman, most of the audience will be following your talk via YouTube, and we are sure that his insights enrich has all. Professor Charles Pfefferman, thank you so much for accepting the invitation, and you can start.
Okay. Do you hear me?
Yes.
Yes. Okay. So first of all, thank you for the laudatory introduction. It's a pleasure to take part in this conference, including several of my old friends. Now, let's see. All right. I thought that today's topic, I'm sorry, this hour's topic is going to be a flight from reality. We've heard about the complex problems of the real world in the last hour from Luis. This I hope you will find amusing. The topic is intrinsic manifold learning. This is joint work with two grad students, Jonathan Marty and Kevin Wren. Okay. Here's the problem. Suppose that a lot of points, n points, are sampled from a compact Riemannian manifold. We don't know the manifold, but for each pair of sample points, we're given their distance corrupted by large unknown noise. Given that, can we deduce the geometry of the manifold and the location of the sample points? Okay. At first glance, it seems that there's not enough information to say anything useful, but we'll see that, in fact, we can do surprisingly well. So here's the plan of the talk. First, I'm going to carefully formulate the problem, and it's going to come in several different flavors, depending on exactly what we assume. Then I'll state the results, and I'll sketch some of the ideas in one of the proofs. Okay, but before I start in earnest, I don't want to slander anybody, so let me give proper credit. So we're building on earlier work by the authors you see on the slide. I should say that all of the papers that I'm referring to are on the archive. So I won't tell you exactly which page numbers and which journals they appeared in. They can easily.
Professor Herman, sorry
Yes.
to interrupt you. You're not sharing your screen yet.
Oh dear. Oh dear. Okay. Thank you. All right. Wow. Oh dear. Okay. Share.
No problem.
Let's see. There.
No.
Oh, wow.
Okay.
Thank you. Details. Okay. So yes. So here's the first paper, the first two papers, and we build on that. In particular, these people solved the problem of reconstructing the manifold if you know exactly the distances between the points. And then that was the first paper. The second paper deals with large noise, but making particular assumptions on the nature of the noise. Now, I wanted to mention also that our techniques overlap significantly with earlier work of these three authors, and here are two of their archive postings. Okay. Okay. Our results, well, our first results appear in this one archive posting, and stay tuned for a second archive posting to appear soon. Let's see, what's the definition of soon? Perhaps in a couple of months. Okay, so let me try to formulate the problem carefully. So here's what's happening unknown to us. We have a Riemannian manifold. There. Let's get rid of there. We sample a whole lot of points from the Riemannian manifold, let's say uniformly at random with respect to the natural probability measure on the manifold. The manifold is compact. Then this D denotes simply the distance from one sample point to another in the manifold. But we don't get to see any of that. Instead, there is a random process which corrupts the actual distances, D, and produces noisy distances, D prime. And so for each pair of sample points, there is a noisy distance. And part of what is unknown to us is how this random process works. Let's normalize so that the manifold has diameter 1. We fix its dimension, that's lowercase n. I'm going to think of the size of the sample in two different ways. There can be capital N, that's the number of sample points, but I'm also going to think that this capital N is epsilon to the minus the power of the dimension, so that roughly speaking, these points form an epsilon net inside the manifold. Okay. So epsilon is the natural length scale that these points seem to determine. Okay, now we're given the noisy distances, and our problem is to recover the true distances and the Riemannian manifold as accurately as possible. Now we're going to allow noise comparable to the diameter of the manifold. So just I don't know, a little example to imagine. I think the diameter of the Earth by as the crow flies, is of the order of 15,000 kilometers, right? Right, and the area of the Earth is of the order of 10 to the 8th square kilometers. Imagine that 10 to the 8th points are sprinkled on the surface of the Earth, and you are given the distance between any two of them, but corrupted by noise, and the magnitude of the noise is 10,000 kilometers, comparable to the diameter of the Earth. Can we actually say anything about where the points are? That's an easier version of the problem because we know the manifold M, it's the surface of the Earth. So, all right, we don't know how the noise is produced. We don't assume that the noise is unbiased. So the expected value, the mean of the noisy distance, is not necessarily equal to the true distance. And the take-home message from the talk is that although it seems that there's not enough information to say anything useful, in fact, one can do surprisingly well. And as we'll see, how well we can do depends crucially on exactly what we assume about the smoothness of the manifold and the smoothness of some auxiliary function that will appear in a few slides. All right, so the relevant assumptions that we might make pertain to the manifold and the noise. So first, let's talk about possible assumptions on the manifold M. Well, we could make minimal assumptions. These are the assumptions that tell us that our M is a metric space with a probability measure, and it looks a little bit like a Riemannian manifold. So, for example, the volume of a ball of radius r is at least of the order of magnitude that it should be in Euclidean space. Okay, this second assumption says that given any 2 points, there is a midpoint between them. So you look at the geodesic joining x and y on a manifold. Maybe there are lots of such geodesics. You pick one of them, and on that geodesic there is a midpoint. So there's a point z whose distance from either x to y is half the distance from x to y. And finally, given any 2 distinct points, the volume of this region is bounded below by a constant. So this region consists of points z whose distance from x, or the distance from our z to x, and the same z to y, those distances differ by at least a small constant times the distance from x to y. The next slide shows why that's true. So if x and y are close, as in this part of the slide, then there's a cone here, and all of these points are noticeably closer to y than they are to x, and the difference between those distances is of the order of the distance from x to y. That's what happens if x and y are close, so that the manifold looks like Euclidean space. If x and y are far apart, so that we don't really know how the manifold looks, we can simply draw a ball around x, and all of these points are much closer to x than they are to y. And so that's why those assumptions are reasonable for anything that looks roughly like a manifold. But as you see in this slide, there are also non-manifolds for which those assumptions are true. So here's a sphere, or maybe the surface of a potato. Here's a slightly more complicated manifold. Here's a cone. Here are 2 planes. And those assumptions hold in such cases. And so we should try to denoise distances and recover geometry in that setting. Well, those are the minimal assumptions we could make on the manifold. Somewhat stronger assumptions I'll call reasonable geometry. And so those pertain to some concepts from differential geometry, sectional curvatures, and injectivity radius. So I want to assume that the sectional curvatures are bounded and that the injectivity radius is bounded below. I think it would be reasonable to review the definitions since people here don't necessarily specialize in differential geometry. But instead, I just want to give examples of what kind of behavior is being ruled out by those assumptions. So the bounded sectional curvature assumption rules out something like this. So imagine you have a manifold which has a sharp tip here. Well, if it were perfectly sharp, it wouldn't be a manifold at all. But if the tip is only very, very slightly rounded, then this is a manifold, but something is wrong with its geometry. It has that tip, and we could assume that the manifold is sufficiently smooth that it doesn't look like that. On the other hand, the injectivity radius assumption rules out things like this very, very thin cylinder. And I mean, it's a two-dimensional manifold, but if you look at noisy data, you could be forgiven for thinking that it's actually a line segment. So we could rule that out. So those are the sort of intermediate assumptions. And finally, we could make strong assumptions on the manifold, which you see on the slide. And roughly, simply, the manifold is very smooth and it doesn't look like a spaghetti. Okay, so those are the assumptions on the manifold. Next, I'd like to talk about assumptions on the noise. I should say, please feel free to interrupt if anything isn't clear. I tried to make everything perfectly clear, but if I fail, please stop me. Okay, so to begin with, let's assume that the noisy distance between any 2 points is bounded. Now remember, I've normalized my notion of distance, so the diameter of the whole manifold is 1. And so I'm saying that the noise is at least not large compared to the maximum distance between any 2 points. I also want to assume that conditioned on the positions of the sample points, the random variables, the noisy distances, are mutually independent. So each distance is corrupted by independent noise. Okay. Moreover, I'm going to assume that once you condition on where the points are, the expected noisy distance is at least a function of the true distance. Okay. But this function is unknown. It's presumably increasing. I would like to assume that if 2 points, if distance actually increase, then at least expected noisy distances increase. So this unknown k of t is an unknown increasing function of one variable. And now what else might we assume? Well, again, there are minimal assumptions, stronger assumptions, and strong assumptions. So the minimal assumption is that the k is bi-Lipschitz. So for example, let's say its derivative is bounded above and below. It isn't necessarily differentiable everywhere. Maybe it has a kink or two. Or we could assume that this function k is C2. So we keep the bi-Lipschitz assumption, but we also assume that it has 2 bounded derivatives. Or we could assume that k is simply smooth. It has a lot of bounded derivatives. Okay. And so that means that our problem comes in several flavors. So for each flavor, we're told which flavor we're dealing with, and we're given a whole bunch of noisy distances d prime, and we're given those constants that enter into our assumptions, and we're given the dimension, let's say. Probably you can infer it from the data, but let's not bother. Let's say the dimension is given. Okay, and then our problem is to recover the true distances and the manifold. Okay, now the results are going to take the following form. First of all, we're just going to discuss how to pass from the noisy distances to the true distances. Once we can do that, we can plug into previous work. And thanks to the work of Ivanov, Kirilev, Lasas, Narayanan, and me, that old paper, we can then reconstruct the manifold. So once we can denoise the distances, it's known how to reconstruct the manifold, and so we'll just talk about denoising. So here's a picture. Imagine that you have a manifold and you have all those red dots, and the distances between them, you can imagine that one can then reconstruct the manifold. Okay. Now for each of the several flavors of the problem, that means for each of the various assumptions on M and on this function K, here's what we're going to produce. We're going to exhibit an algorithm that runs in polynomial time and produces numbers that I'm going to call decomputed. We guarantee that for any pair of sample points, the computed distance differs from the real distance by some small number that we specify. And that's going to be true except for a disaster. Now you can't rule out a disaster if you're sampling points. Maybe you sample 1 billion points on the surface of the Earth, but maybe all of these billion points on the surface of the Earth are located near the North Pole. If that's true, you're not going to be able to say anything about what the Earth looks like. So I want to rule out a disaster, but the disaster should have probability less than the number of sample points raised to the power, let's say, minus 100. And this is such a negligibly small number that we can safely assume it won't happen. Okay, so that's what it means to solve the problem, and we will then say that we compute the true distance up to a specified accuracy, the specified accuracy being this number, the bound for the difference between what we compute and the actual distance between sample points. Okay. All right, so here are several theorems. First of all, if you make the minimal assumptions on the manifold and the minimal assumptions on this function k, then we can compute the true distance to this accuracy. Now, I'm going to ignore all powers of logarithms and just concentrate on the power of epsilon. Remember that the meaning of epsilon is that if you pick a large sample, that sample is approximately an epsilon net, where epsilon is some appropriate power of the number of sample points. And in this case, the power is this number, where remember little n is the dimension of the manifold. So for example, if the manifold is, say, two-dimensional, this p is what I think it's 1/3. And as n gets large, as the manifold gets higher and higher dimensional, this is approaching a half. So not as good as epsilon, but nevertheless epsilon to a power. Okay, the next theorem is not due to us, but to the team of Mossel and his collaborators. And it's based on the following stronger assumptions. So suppose that M has bounded sectional curvature and injectivity radius bounded below. So remember, those are the medium strong assumptions on the manifold. But regarding this unknown function k, we only assume that it's by Lipschitz. Then they can compute true distances to this accuracy. Again, forget about logarithms. The power of epsilon is better. In particular, notice that when the dimension is at least 6, this fraction is bigger than 1, and so we get accuracy actually better than epsilon. So even though our sample points approximately form an epsilon net, nevertheless, Mossel et al. Can get better accuracy than epsilon. They get epsilon to a power higher than 1. Okay, well, now again, as in the previous theorem, let's suppose that M satisfies the medium strong assumptions, bounded sectional curvature and injectivity radius bounded below. But now let's suppose that this function k of t is C2. Well, then you can compute the true distances to yet a better power of epsilon. And now we find that when the dimension is at least 3, the accuracy is better than epsilon. And when n equals 2, it seems to me n equals 2 and n equals 3 are the most appealing cases. And then when n equals 2, this fraction works out to 1. And so we recover accuracy epsilon up to that log. All right. But in fact, we can do more. We can get the same accuracy for all pairwise distances, but not merely for the original sample points, but for a net of this length scale, of this same length scale. So even though our sample points form only an epsilon net, we can compute pairwise distances for a finer net. And here's a picture to illustrate what I mean. So here's a picture of a manifold. The black dots represent our sample points, and the red dots represent points that we will compute, and we will compute all the pairwise distances between the red dots. Okay, well, all right, those were the medium strong assumptions. How about the strongest assumptions? So let's suppose that M is very smooth and K is very smooth, and in that case, we can compute true distances for our sample points and for a finer net, as in the previous result, up to this accuracy. So now it's epsilon to the power n over 2. Again, when n is 2, guess what? N over 2 is 1, and so we recover the accuracy of the net that we started with, and in dimensions higher than 2, we do better. Okay, so that's epsilon to the n over 2. Well, that's what our algorithm does. What might some other algorithm do? And the answer is that there is a no-go theorem, even if you assume that you know that your manifold is the usual sphere with its usual round metric, nevertheless, no algorithm can compute true distances more accurately than epsilon to the n over 2 divided by a power of epsilon. So, I'm sorry, a power of log epsilon. And so up to log factors, this epsilon to the n over 2 is just the best one can do. Okay, well, those are the results. I found them surprising. Okay, I'd like to show you the ideas, some ideas from the proof of one of the theorems. So I'm afraid I'm only going to have time to explain ideas from the proof of the first theorem. Minimal assumptions imply that you can recover true distances up to the accuracy of some power of epsilon, but not as good as epsilon itself, instead epsilon to this power. Okay. So let me just recall. Before I do, all right. So I'm not going to be able to get into the proof of what one can do with stronger assumptions, but let me just say that if you want to make use of stronger assumptions, hold on. If you want to make use of stronger assumptions, the first thing you do is that you apply theorem 1 so that you get a crude understanding of what the manifold looks like and what the distances are. And then you do further work with other ideas in order to refine the understanding. Okay. Well, all right. So we're dealing with minimal assumptions. Let me just remind you what they are, because maybe these slides have gone by quickly. So the volume of a ball is at least what you think it ought to be. Given 2 points, there is a midpoint between them, and there is this geometrical condition that if you have 2 points that are not the same, then there's a large set of points z whose distance to x is noticeably different from the distance to y. Those were the minimal assumptions. Okay, and now there will be a brief pause while I kill this set of slides and pass to the next one. Let me see, where is that? There we go. Okay. Okay, so under those assumptions, what we want to do is recover the true distances up to a small additive error. How are we going to do that? Well, here's the plan. First, we're going to decide whether 2 given sample points are close to each other. Once we do that, we can gather the sample points into point clouds, which I'm going to denote by C sub nu. Nu is the index set, C sub nu is the nth point cloud. Okay. Using the point clouds, we're going to compute the expected noisy distance, which remember is given by this formula up to small errors. So, well, we want the true distance, and so far we have k of the true distance, and so the next step is to peel off k and to pass from k of the true distance to the actual true distance up to a small error for each pair of sample points. Having done that, we declare victory. That's the plan. Okay, how shall we carry out the plan? Well, all right, the first step is to decide whether 2 given sample points are close. And the key idea is this. As a substitute for a given sample point, we consider the function on the slide. So as a substitute for x, we consider the function f sub x, which takes y to the expected noisy distance from x to y. And so that's defined for each sample point y. Now, we can't actually compute that function because this k of the distance is merely the expected value of the observed noisy distance and not the noisy distance itself. So our big idea to use f sub x runs into the embarrassing problem that we cannot compute it. However, we can compute inner products of 2 of them. So if we take 2 points x and x prime, then we can define their inner product to be the sum over all the sample points y of the product of fx at y with fx prime of y. Let's normalize that by dividing by the number of sample points. That was our n. Okay, and we can essentially compute this because this sum is the same as this sum. I just wrote out the definition of the f's. And that is approximately the sum of the product of these noisy distances, because here we have a sum of a whole lot of independent random variables, and if you take a whole lot of independent random variables, you may not be able to say much about any one of them, but when you add them all together, it's very likely that the sum will be relatively close to the sum of the expected values. And so by the law of large numbers, this thing that we want is very close to this, which we can observe. But there's a glitch. I've got to assume that those 2 points x and x prime are distinct because up here I've used the fact that the expected value of the product is the product of the expected values. If x and x prime are different, then these random variables are independent, and so we're in good shape here. But if x and x prime are the same, then this approximation would ignore the standard deviation of the noisy distance. That's very bad. So if x and x prime are distinct, we can compute their inner product. We can compute this inner product, but unfortunately, if x and x prime are the same, we can't. Well, okay, so now we know about inner products. How are we going to apply inner products? Well, what we're trying to do is to decide whether two given sample points are close. And so in order to do that, let's look at the norm squared of the fx minus fx prime. So that's of course the inner product of this thing with itself. And the idea is that if x and x prime are close, then for all y, the distance from x to y is close to the distance from x prime to y. And therefore, k of the distance from x to y is close to k of the distance from x prime to y. And therefore, fx minus fx prime is small, and therefore its norm is small. So if x and x prime are close, this norm is small. On the other hand, if x and x prime are not close, then then one of our assumptions says that there's a whole lot of points y for which the distance from x to y and the distance from x prime to y are not close. And therefore, k of dxy is not close to k of d of x prime y, and therefore fx minus fx prime is
Sorry,
not small.
Professor Pfefferman, the new slides are not appearing. Sorry.
Oh dear, how long has that been true?
47.
All right, let me see what I can do. Wow.
More ahead.
All right, wait a minute. Where? Oh dear. Oh, what a mess. What is that? Let's see. Nope, I should get rid of that. Let's move it. All right. Let's move that. Come on. Oh dear. Now what's this? Nope, 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 nope. What's this? No. All right, let's move this. I apologize. I don't know what's going on. Computers are my enemies, as you can tell. Huh. Oh dear. I don't know what to do.
Maybe you can try to stop sharing and share again, Professor.
All right. Yes. All right. Stop sharing. Very good. Very good. Later. And now I will share again. Okay. And I'm sharing. Let's see if this is the right thing. Yes. That's the right thing to share. Let's share that. Okay. Okay. Can you see that? Can you see my screen?
Yes.
Wow. Okay. Should I go back a couple of slides?
I think it's better, Professor. So
Okay.
sorry.
No. I'm sorry. Wow. All right. Tell me. Let's see. Tell me when a slide looks familiar. I should go back over all of these? Okay. Okay, here goes. Sorry.
Is
Hello?
That's okay.
That's okay there?
Yes.
Okay. So the first step was to decide whether two given sample points are close. Okay. And the key idea is to use as a substitute for a sample point x this function f sub x, which you see on the slide. Remember that k of this distance is the expected noisy distance, and so this is a function of sample points y. So fx is a function of sample points y. Okay. Unfortunately, we can't compute it because this thing is merely the expected value of the noisy distance. We don't know the expected value of the noisy distance. We see only the noisy distance itself. And if you see one instance of a random variable, you don't know the mean of the random variable. But we can compute inner products defined this way. So given 2 points x and x prime, we add over sample points y, fx of y times fx prime of y. So that's a natural inner product. And you normalize that by dividing by the size of the sample. Now, let's see, this can be computed even though the sum can be computed to very good approximation, even though the individual summands cannot, because this sum here is the sum of the expected value of these random variables. And by the law of large numbers, when you add together a whole lot of independent random variables, even though each independent random variable doesn't indicate much about its expectation, nevertheless, the sum is going to be very close to the expected value of the sum, which is this. So we can compute inner products. The only thing is that x and x prime had better be distinct, because I'm assuming that the expected value of this random variable is equal to this number. That's true by our independence assumption if x and x prime are distinct, but if x and x prime are the same, then it fails with a vengeance. So we can compute inner products only fx without fx prime, only if x and x prime are distinct. Okay, so that's what we can say about inner products. Now we want to use inner products. Remember, the goal is to decide whether two given sample points are close. And the idea is that we're going to look at the norm square of the difference of those functions, fx and fx prime. On the one hand, if x and x prime are close, then for all y, the distance from xy is going to be close to the distance from x prime to y. And therefore, k of the distance here is close to k of this distance with an x prime, which means, by definition of the f's, that fx minus fx prime is small everywhere, and so its norm is small. So if x and x prime are close, then the norm of this difference is small. On the other hand, if x and x prime are not close, then there's a whole big set of y such that the distance from x to y and the distance from x prime to y are noticeably different. They are not close. And therefore, k of this distance is not close to k of that distance, which means by definition of the f's that fx of y minus fx prime of y is not small, and that's true for a big set of y, and therefore this norm is not small. So that means that x and x prime are close if and only if the norm squared of fx minus fx prime is small. And we hope to compute that using inner products. Oops, well, here I've expanded out the norm squared of the difference. And of course, it has two cross terms, but it also has these two squared terms. And we just decided that whereas these two can be computed to high accuracy, these cannot. So it was a nice idea, but it doesn't work. But we're going to fix it. Here's the fix. Let's consider inner products of the difference of these two f's with the difference of these two f's, where I've introduced two new points, z and z prime, and we suppose that these are all distinct. Okay, now when we expand that out, we are never taking an inner product of one of the f's with itself, so we can compute all of them. We can compute all of these inner products to high accuracy. Now, if this norm is small, then of course this inner product is going to be small. The inner product of something bounded with something small is going to be small. On the other hand, if this isn't small, we could take z very close to x and z prime very close to x prime. And so this difference of fz's is very close to the difference of the fx's. And therefore, this inner product is very close to the norm squared of the difference of the fx's, and that's not small. And so x and x prime are close if and only if this maximum is small. Okay, and that's something that we can compute. It's very easy to do better. We don't have to look at all possible zz prime. We could just look at fz, but never mind. We've carried out step one. We have figured out in polynomial time whether two given sample points are close. Okay, step two was to make point clouds. What we want these point clouds to do is the following. First of all, each point cloud consists of sample points. Every sample point is contained in at least one point cloud. Each point cloud has diameter small compared to 1. Remember, 1 is the diameter of the whole manifold. But even though it has small radius, nevertheless, it contains many points. And of course, if we have a very large sample yielding a very fine net, such point clouds should exist, and we want to be able to compute them. And in fact, it's easy to do so because step one tells us which sample points are close. And if we know which sample points are close, we can just gather together all the sample points that are close to, let's say, a given sample point, and that will be one of our nice point clouds, C nu. So now we are armed with a whole lot of point clouds C nu. All right. The next step is to use the point clouds to compute k of the true distance for each pair of sample points modulo a small error. Okay, so remember this is the expected noisy distance. What we started out with was simply the noisy distance itself, and now we want to understand the expected noisy distance. All right, and so to do that, we remember that k of the true distance is the expected noisy distance. So it's the expected value of something, and we're going to exploit, again, the law of large numbers. So given any two sample points, we find point clouds. Let's say C mu contains xi, and C nu contains the other one, xj. Now, since these guys have these these clouds have small diameter, we expect that for any points x in the point cloud C mu and y in the point cloud C nu, the distance from x to y is going to be very close to the distance from xi to xj, and therefore the k of the distance from x to y is going to be very close to the distance from xi to xj, and this is the thing that we want to understand. Given that, well, since C mu and C nu contain many points, we can argue as follows. Here's something we can observe. We've calculated the point cloud C mu. We know which points it contains. We know which points this contains. And we sum over all x and y in their respective point clouds the noisy distance which we can observe. So this is something that is under our control. We observe this directly, and we've computed these guys. And by the law of large numbers, since we're summing a whole lot of independent random variables, that's close to the sum of the expectations of these guys, which is therefore, and not just approximately, it is equal to the sum of k of the true distance. The expectation of the noisy distance is k of the true distance. But remember, for each x and each y in their respective point clouds, this k of d of xy is close to k of d of the sample points xi with xj, and so this whole big sum is comparable to the number of points in the point cloud C mu times the number of points in the point cloud C nu times the fellow we want, namely k of the true distance from our sample points. So k of the true distance between our sample points is very close to the average, the mean over all the pairs x, y in their respective point clouds of the noisy distance. And so, all right, this can be computed once we know what the point clouds are. And so we have succeeded in finding k of the noisy distance. Okay, and so step 3 is complete. Well, now we know k of the true distance, and so step 4 to finish the game is to peel off k. So given approximate knowledge of all of the numbers k of the pairwise distances from the sample points, okay, given all these, we want to compute the d's themselves up to a small error. And then we will have denoised the distances. Okay, well, so there are three steps in doing that. First, we're going to bisect geodesic line segments. Then we're going to make a ruler. And finally, we're going to use the ruler to read off distances. So, okay, let's look at those 3 steps. So given 2 points x and y, I would like to compute a midpoint. So I would like to compute a point z whose distance to either x or y is very close to half the distance from x to y. Such a z is not necessarily unique. Think of the North Pole and the South Pole on the Earth. But I would like to compute, given x and y, at least one z that satisfies this condition. Okay, well, here's how we compute such a z. The exact midpoint minimizes this function. Okay, given any z, look at it, the maximum of its distance from x and its distance from y, and take the maximum of those 2 numbers. And we want to minimize that, and that is minimized by the exact midpoint. Well, that's the same as the minimizer for this function, which now involves not the true distance, but k of the true distance. And we have computed k of the true distance from the previous steps. So in principle, we're in very good shape. Of course, we can't inspect all points z in the manifold, only sample points. However, the sample points form a fine net in our manifold, and so the z that we pick will simply be the sample point that minimizes this function of z. And so from our previous work, we can compute that. And so now we know how to take the midpoint between 2 given sample points x and y. Okay, so we can bisect line segments. Well, once we can bisect line segments, we can make a ruler. Now, what is a ruler? A ruler is a collection of a whole lot of equally spaced points on a straight line, or at least on a geodesic in a Riemannian manifold. So starting with 2 points x and y, let's say the distance between them is L. We don't know what L is. But given 2 points x and y, we can repeatedly bisect starting from the geodesic joining x to y. And so here's a picture of repeated bisections. You know perfectly well what's going on here. So here are x and y to start with. We bisect the line segment between them, producing the red dot. We bisect this line segment to produce this guy. We bisect this line segment to produce this guy. Let's see, next. Let's see. Oh, I must have been asleep. Step 3 is the same as step 2. Well done, Charlie. But then at the next step, you bisect this and you insert that guy, you bisect this, you insert that guy, and so on. And so now look, we have a whole lot of equally spaced points, and we can repeat this as many times as we like until our slight errors are comparable to the distance between successive points. And so we have produced a ruler. Okay, now that we have a ruler, let's use it. Well, okay, remember, starting from our 2 more or less randomly picked points x and y, whose distance apart is some unknown number L, we made a ruler, and the ruler consists of equally spaced points that I'm now going to call x0, x1, and so on through x2 to the m for some large m. M is the number of times we've performed the bisection. And so because the points are equally spaced, we know that the distance from x0 to, let's say, the lth point is equal to L over 2 to the m times this unknown length, capital L, and that's true for all little l from 1 to 2 to the m. And that's true with high accuracy. Okay, so all right, we know that this is true to high accuracy. On the other hand, from step 3, we also know k of the true distances, and so we know these numbers. We know these numbers kappa sub L. So on the one hand, we know the true distance. Well, we don't know this number, but except for one scaling factor, we know all these distances and we know all these numbers. And so it's maybe most convenient to look at the inverse function to our unknown k. K inverse of kappa L is equal to this guy for a whole lot of very closely spaced points kappa L. And so in effect, we have computed K inverse up to an unknown scale factor, L. Well, how are we going to recover that scale factor? It's easy. The scale factor is determined by our normalization. We declared that the diameter of the manifold is 1, and we now know all distances on the manifold, or at least all distances among the sample points, up to a scaling factor. We adjust the scaling factor so that our manifold has diameter 1, and then we're done. So we've computed the function K inverse, and we also knew before K of the true distances. And so combining this information, we can then read off all of the true distances modulo small errors. Step 4 is complete. And so step 5 was to declare victory. Okay, we hereby declare victory. Starting from the noisy distances, we have computed the true distances modulo a small error. The proof of theorem 1 is complete. And here's a little summary of what happened. To start with, we computed a lot of inner products, fx with fy. We used those to determine whether two given points are close. We used, we used that knowledge to make, very simply, to make point clouds. We used point clouds to exploit the law of large numbers to compute expected noisy distances k of d for all pairs of sample points x and y. Using that, we were able to bisect geodesic segments. Using successive bisections, we made a ruler. Combining the ruler with our knowledge of k, we were able to compute the inverse function to k. I'm sorry, here we know k of the true distance. And putting this together with that, we obtain knowledge of the inverse function of k. And then because we have k of the true distances and the inverse function to k, we can read off the true distances. So that's what happened. Okay, so of the various theorems, I showed you, I think, the ideas in the proof of one of those theorems. All right. So we've seen the proof of theorem 1. The other theorems assume, I really was asleep. Theorems 2, 3, and 4 assume a stronger smoothness condition on the unknown m and k and compute true distances to much greater accuracy. The algorithms promised in those theorems start by applying the algorithm of theorem 1 and then doing substantial extra work. There's no time here to explain the ideas in those algorithms. And there's also no time to explain the proof of the no-go theorem. I just want to recall a couple of the theorems. Under the strongest smoothness assumptions on m and k, this is how well we can recover the true distance. And there was a no-go theorem that says that essentially you can't do better than that up to logarithms. So those are the results. And thank you for listening. Thank you in particular for your patience with my computer incompetence.
Thank you, Professor Charles. Now we have some minutes for questions from the audience. Feel free to post your questions in the chat. Here we have a question. Someone asked the following. This may be a naive question, but how does the small error in slide 26, Professor
Oh my God.
Charles?
What was
And
slide?
how,
Oh, I'm sorry.
26. And
Yes.
how can it be measured?
Oh, okay. Part of my computer incompetence is that I'm not sure which is slide 26.
Okay.
Okay. Can someone tell me what was on slide 26?
This is before or before 20.
Here.
Oof.
All right, we're getting to 26. There are two sets of slides. So let's see.
Sí, sorry.
There?
Not.
Not that one. Another
No.
slide, 26.
Okay, no problem.
Oh dear.
Okay.
Maybe I talk in general about how small
Yes.
these small errors are. Okay, so there are two sources of error. One source of error is simply that, for example, if you have suppose that you have 3 points x, y, and z, and you want to approximate the distance from x to z by the distance from y to z. Okay, that's something that happens over and over and over again in this discussion. For example, replacing a sample point by something in its point cloud. In that case, the error is simply controlled by the radius of the point cloud, okay, which you get to pick. So you get, roughly speaking, you get to, well, you get to pick an upper bound for the size of the point cloud. That's one source of error. Another source of error comes from the law of large numbers. So if you take n bounded random variables and average them, then the error that you make is of the order of 1 over the square root of n, right? Basic statistics. So imagine, for example, you wanted to pick the size of a point cloud. The larger the radius, the larger the geometric error arising from the triangle inequality. But the larger the radius, the smaller the error arising from statistics, because a ball of large radius has more points than a ball of small radius. And so you do some optimizing. You pick the radii of your point clouds in such a way that there is a balance between the statistical error and the geometric error. That's a slight oversimplification because you don't actually know the radius of the point clouds. You know only you know that with very high probability the point clouds are contained in a ball of some radius and they contain a ball of some smaller radius. But nevertheless, you use the larger radius to estimate the geometric error and the smaller radius to estimate to estimate the statistical error. And those considerations apply right down the line, and I mean, because there are enough steps, there's a fair amount of calculation you have to do in order to optimize everything. But the errors arise from stuff like that. If you make differential geometric assumptions, so instead of just theorem 1 with minimal assumptions, if you assume more smoothness, then there are additional considerations. For example, suppose I have a small point cloud. And so it contains many points, but it's small. And I pick some faraway point. I look at I want to understand the distance from the, suppose I average the distance from the outside point to the points of the point cloud. Well, to pretty good approximation, that's equal to the distance to any one of the points in the point cloud, because the point cloud is small. But you can do a lot better than that. You can try to take the distance to the center of gravity of the point cloud, and that's much more accurate. And if you fuss with that idea, you can do much better. That's maybe the fundamental difference between the theorems I haven't explained and the theorem that I did explain. And there, the geometric error is different. It's not just from the triangle inequality, it's from some differential geometry. I hope that answers the question sufficiently.
Okay, thank you so much for exploring more this question. We have a couple more questions. Assuming necessary condition on M, it is possible to approximate the eigenvalues of the Laplacian using the distance?
Oh, yeah, once, okay. All right, I believe that once you are given a lot of points randomly sampled on a manifold, exactly on a manifold, you can then it's known how to understand um, eigenvalues and eigenfunctions of the of the Laplacian. And in fact, right, that's a standard thing to do in manifold learning. Um, but um, all right, that's assuming exact knowledge of the placement of the points on the manifold. If you assume small errors, depending on how small, and I don't know, it may be known, but not to me. If you assume small errors in the placement of the sample points, then presumably you can do almost as good a job as with exact knowledge. And what we're talking about in this talk was getting rid of large noise.
Okay, okay. Professor Duan asked the following. In Theorem 1, do you know about the evidence that could impose a weaker condition to the one of the Lipschitz condition on the manifold M?
Oh, that's an interesting question. I don't know about that. I think it would be natural to well, I mean, a very bad example would be, let's say, if the expected value is constant, right? Uh, but there could, for example, be intervals of constancy, and then one would have to take the geometry into account, maybe in a more serious way. That's a very interesting question. Thank you.
Okay. Thank you, Professor Pfeffer. Duvan ask again, if instead of having the distance for the Riemannian metric, and if one consider a sub-Riemannian metric coming from Hormander vector fields, is there literature for the reconstruction of distance?
Oh, let's see. I believe that our theorem one would apply, not any of the others. Is there a previous literature? I don't know. Again, thank you for the question.
Okay, okay. Professor Pfefferman, I have a small comment. I don't know if could you talk a little bit about the possible application. For instance,
Oh,
I imagine that theory of intrinsic manifolds can be applied to improve medical images techniques where that data often comes with noise and incomplete measurements, I
sure.
think.
Sure. Okay. Oh, thank you for that question. Yeah, that was certainly the motivation for this. So the first paper that I mentioned at the beginning of the talk uh, um, uh, gives gives a way to reconstruct a manifold from exact distances, and that's motivated by work of Matti Lassas, um, who considered reconstructing the inside of, let's say, the human body from measurements made on the surface, as in, for example, ultrasound. Um, let me not pretend to understand anything about ultrasound. Um, uh, so I think in order to make use of this, it would be great to weaken very significantly the assumption that all of these pairwise distances are independent. That is the noise, independent noise. The actual noise is probably not independent in application. So this is, in that sense, a toy problem. Um, there is a natural, more general hypothesis in which, for example, suppose you have pairs of points, let's say x1, y1, x2, y2, and so on, xn, yn. And if all of those points are distinct, then the
Yeah.
distances from the x's to the y's are mutually independent. That's a very realistic, reasonable assumption. But unfortunately, um, we can prove that 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 is that no algorithm can place the points. It's not known whether, given sufficiently strong geometric assumptions, the manifold could be reconstructed, but you definitely cannot place the points. Here, maybe I'll stop sharing. Whoop. Yeah. So there.
Okay.
Yeah. But yes, certainly. I mean, this maybe the thing to say is that this feels sort of related to problems of medical imaging, but the assumptions are too strong for it to be directly applicable.
Okay. Thank you, Professor. I am very surprised by the role of the law of gray numbers in your research.
Oh, thank you. I
Very
want to
interesting.
say
Very interesting. Yeah.
thanks. So
Oh.
I mean, I got interested in this problem just because I thought the question was fun, and I found the answer surprising. So I hope that you've been amused by the talk, even though the assumptions are too strong to have practical applications.
Okay, Professor. Thank you, Professor. There is no more questions. Adrian Franco said, thank you, ICMAM, for bringing us such a great talk, like Charles Pfefferman. Amazing.
Amazing. Well, thank you.
Okay. Okay, thank you for sharing with us your research. For us, it's a very nice opportunity to know about your project, your research. And thank you so much for participating in this Congress, Professor Charles.
Thank you. A pleasure. Well, now I will go collapse. So thank you all for listening.
Okay.
Bye-bye.
Okay. Thank you, Professor Villamizar, and thank you to all the speakers and everyone in the audience for joining us on this fourth day of the ICMAM Latin America 2026 conference. Remember that tomorrow will be the last day of this conference. We will start with the talk by Professor Michael Rusanski, and we will have many other excellent talks during the day. I would especially like to invite you to attend the closing session where we announce the ICMAM Prize 2026. Thank you very much and see you tomorrow. Bye-bye.
See you. Bye-bye.